You may be the host, Eddie. Eddie, you
Yep.
may, yeah.
Hi, everyone. Thanks for coming back. This was kind of an interesting number. This is Ken Shoulder's number 51. And we know that Pete Peterson and Chris Beskar were together there. So interesting number. And what we're going to do is go through some more of the tube stuff and talk about some of the vacuum tubes that we were looking at last time. And what I did is I went in and I grabbed the tube data sheets for some of these tubes, and then everyone can jump in, but Paul especially will know a lot about, and Alan will know lots about what's going on here. So this was one of the tubes that Moray had asked about what kind of gas is in it. So the after we go through this, there is a slide that actually shows what kind of gases in each one of these, and it's slightly different for each one. So some of the interesting things is, see how it says electric cathode is cold. Now, most vacuum tubes are considered sort of a hot cathode. So, Alan and Paul, what do you think about that?
Yeah. Well, what that means is most cathodes are a filament, like it's like a light bulb, and that's what creates the electron cloud to travel through the tube to the plate.
Yeah.
In a cold cathode, it's not heated. That's the thing. It's not lit up like a.
So is it just set at a voltage potential?
Yeah,
And
yeah,
okay,
yeah,
okay, wow.
Mhm. And that
Could
means it's hard to get the electrons to emit. They
yeah,
don't want to emit from the plate, and that's why cold cathodes are unusual.
yeah,
yeah.
yeah.
And see, it also says miniature glow discharge type. So what is that referring to?
So the gas, once there's enough voltage potential across the gap, so it's like regulating the voltage, kind of like a diode. And once the gas breaks down, there's a certain point, so you can raise your voltage up, and then all of a sudden the gas will break down, and then current flows.
Oh,
So,
okay.
so that's why, yeah, it starts to glow then when the
Yeah,
When,
electron.
it's a pre-arcing regime.
Yeah,
Right. Paulo Correa really made his invention based on that. He called it the anomalous glow discharge. And it's prior to the spark or prior to the discharge event. You build up all this glow plasma. It's also used in hollow cathode switches where you build up a lot of glow plasma so that the switching event, a ton of electrons get emitted all at once. They don't
yeah,
have to trickle out. And so it's a very important regime because that is the regime where you can launch the ball lightning from that glow plasma discharge. And
oh,
that's what Korea was investigating. And
wow.
he said that discharge was the important thing. And any spark, any current flowing after that original precursor discharge needs to be quenched because there's excess energy in that anomalous glow discharge, the front edge of that discharge. And that's, of course, where we're launching the ball lightning event or EVOs or whatever's coming from the plasma. And
Yes.
Korea made a thorough investigation of these types of tubes. And when I ask about the gas and the plasma, I'm thinking in terms of what T. Henry Moray was doing and what
Yeah.
he had plasma tubes, not vacuum tubes.
Yeah.
yeah,
And so that there's very important new science going on, mainly around the EVO launches,
Yeah.
around these building up the glow and the abrupt event of switching.
yeah,
Yeah.
And so is this cathode? This cathode's a voltage regulator, so it's not meant to switch, right? It's not a switching tube.
yeah. It's more like a diode. It's a regulator. Yeah,
Yeah.
Well,
Exactly.
if it's like a diode, okay.
yeah.
Yeah.
And that's why I use those thyrotrons is because they once they're filled with the hydrogen gas, and so you could put a really large potential across it, and it's not until you make a little teeny spark in the center that spark ignites the gas, then the gas goes from a high resistance to highly conductive, and then the power shoots through, and you get a really sharp rise time, like a big spike on it. And that's the key to launching EVOs and a lot of these things. You just want to have a really sharp front end edge and just pulse power, and that's
Yeah.
what they just emit. Yeah.
That's amazing. So it's pretty interesting that this is the first slide, because I did them kind of randomly, and look at all the good information you guys have coming out of this. Wow. So Brent, let's go on and maybe look more of this. So this is the pinout, and it's the bottom view. So looking at the tube from the bottom, and it is a diode, like Paul was saying, but there is that dot. And I didn't know about that dot until you talked about that, Paul. You can see that it's in there, right?
Yeah.
There's good gas in it.
Anode connection, cathode. Cool. So go a little bit more, Brandon, because it's talking about the currents and the average starting current, 75 milliamps, frequency, there's a temperature. Okay, so there's the typical operation, characteristic range values that they would typically use. And it's just exactly what he's saying there: anode breakdown voltage, anode voltage drop, regulation. So from 5 to 30 milliamps. And yeah, there's always really awesome stuff on these tube data sheets. So 1954,
New Jersey.
Radio, yeah, exactly. Radio Corporation of America.
Yeah.
That's
So that was the big RCA building that was built there, and that factory, the dog, I forget his name,
Yeah.
that's looking in the speaker.
Victor,
or something.
the Victor
Yeah.
thing. Yeah.
Yeah, they had a big manufacturing warehouse there, and they did a big stained glass window in the clock tower of that dog.
Oh, wow.
Yeah, it employed thousands of people all around the area. It was like the major industry there, and they built all the radios and
Yeah.
record players and stuff like that in that place.
RCA, for those that don't know, RCA, like back in the 50s and 60s and 70s, pretty much, was the largest tube manufacturer in the world. In fact, they held most of the patents also. Other companies could build the same tubes, but they had to build them under the RCA standards. And of course, Nikola Tesla is part of RCA.
So what I want to ask is, what is the benefit of a cold cathode? What uses can it have compared to a hot cathode?
Well, that's what we were just talking about, right? These are used to sort of regulate the voltage, and another tube, a hot cathode, like a triode, is actually used for amplification. So it would be like considered an amplifier. But yeah, you were going to say something, Paul, more about that.
Yeah, no, that's what I was going to say. Yeah, because it's cold, it regulates the voltage easier. Yeah.
Right. And you're not emitting electrons. That's the
Yeah,
point.
you don't have
When
a
you
big
heat it, you
huge
want to
electron.
yeah, you're trying to emit electrons. This you're not. You're trying to hold that back.
Limit them.
It's trying to stop electrons coming through so much, that kind of thing.
Yeah.
Until a certain voltage potential hits, and then it does this thing, right?
And you could switch it on, and you may not want that. You may not want to operate it there.
Yep.
So, question for Maury. Has anybody ever seen EVOs in one of these big power amp tubes?
Yeah,
Anything
you actually ask a good question, because Ken Shoulders went to the switching conferences of the IEEE where they're working with hollow cathodes, asking people, have you ever seen it? Because it's a very fast event. So you're going to have to capture it on some type of camera. And now that we have high-speed video, that's where if they choose to look, they'll start to see these events. But all you would see normally just a big flash. That's all you would get out the discharge moment.
Don't we assume, Ed and Maury, that this is where this unique harmonic capability is coming from in an electronic field? Are we actually creating EVOs and dragging longitudinal energy, scalar energy within this tube through the plasma field?
Without a doubt, I think
on the discharge event. It's
on the
event.
discharge. Okay.
It's a very abrupt event, and actually,
so
and
it's
then when
pulsed,
when you get your normal current following it, that's all lossy. Like that's your normal electron conduction that we're used to. So
Right. So
it's
what
the
if I
details of, because every single pulse, every single spark has a little ball lightning precursor on the tip of it. Every
Right.
one.
Yeah, yeah, we
So
had a
that's
highly potentiated environment inside that glass tube in
Um,
a vacuum.
I
So
have,
has anybody ever taken a squid, put it up next to one of these power amp tubes, one of the big ones, with a quasi-complementary, push-pull circuit that's pumping and pulsing, and
yeah, it would be
seen
single-ended.
anomalies?
We'd want to
Yeah.
do it with a single-ended amp, not a push-pull one, because it cancels out all the harmonics. But
Yeah.
that's a good question, actually. We could
but
probably,
but
I've got an amplifier, an 845 triode that we could try that with if you've got the
Yes.
squid, right? So yeah, that's a
Well,
possibility.
I'm still waiting for it. We'll see if it
Yeah.
comes.
Okay, cool.
that's quiz made to be very, very sensitive measuring instrument. You're going to have a abrupt energy event, so you could easily
Yes.
swamp it.
Yeah.
You're not going to
I'm
see
not.
anything. But
I'm
to
not
answer
quite
your
sure how.
question, Ken Shoulders probably is the leader of, I guess, history of studying the details of that event because he's
Mhm.
looking at the front end, what comes off that precursor. His whole focus was on creating the EVO and,
Um,
and studying it.
I,
So there's your source of real deep information on that. And
I,
others have studied it, but they don't have an energy hypothesis behind them. So they go, why bother? Right? They don't want to study looking for anomalies. So
I,
most
So
of the
if we,
engineering community
I,
does not study
so
it.
what is it about, clutching the Z field within a vacuum tube environment, like in a plasma field, that creates the unique acoustic sound in the amplifier circuit? What is
well,
it? Are we stimulating golden
chip,
ratio
chip,
harmonics?
once we get through more of these, I can explain that because that was part of what
Okay.
I'm trying to do here today. So let's keep going with all of this. I was going to say that I have overdriven tubes and seen some anomalies within them, including little blue orbs. So I would almost have to say yes. I've seen them before. I've
Eddie,
also
you shouldn't
seen
have
them.
done that.
I've also seen them laying on the ground looking up. Um, yeah, I've seen them before. I know other people that I've talked to have seen them before as well. Yeah. Um, uh, yeah. Let's keep going, Brendan, because we have quite a few slides. So this just
Right.
goes through the, yeah, you can keep going. This is still the same one tube type, I think. So yeah. So now we're gonna get into, remember we were talking about that 6AL5 and they were used in sort of harmonic cancellation sort of circuits and whatnot, Paul. This is the tube here. And you can see that there's two sections in it. So this is a twin diode. So this is sort of like the one that we were looking at, but different in the fact that a diode basically allows the current only to flow in one direction. That's part of its goal. And we can build different types of circuits. One of them, the best circuit to build is actually a bridge circuit. So there's two sections in here. If you took another tube and connected it into a bridge diode setup, that is your best scenario. But they are operated in different ways as well too, right, Paul?
Paul's muted.
Yeah. Yeah, sorry. Yeah. That one that has two, like the last tube we looked at was like a single diode, and this one it has two in there. So yeah,
Yeah.
you can rectify AC into DC.
Yeah,
Is that resonant frequency correct yet? It says 700 megacycles. We're talking about 700 million cycles. Is that correct?
well,
Yeah,
that's
but you
true.
you'd
Right, seven.
never
Yeah.
Yep.
yeah. So
Holy
you could
shit.
use it. So we have 60 cycles on our regular power. You put it on, it runs at 60, but it will run up to that high for sure.
Yeah.
Yeah.
No
So
kidding. My
yeah.
God.
So that's where they're using probably mostly in radar again. And radar really, if you're talking about electronics, radar is the absolute pinnacle of electronics, essentially, right? Except for maybe the Philadelphia experiment and the FRR 24. But these are tubes that come out of that unit, essentially, that we were looking at last time, right?
So 700 megacycles is 700 megahertz. Is that right?
Yeah.
Yeah.
God almighty.
Yeah. Yeah, and so when people say vacuum tubes are old technology, they don't know what they're talking about basically. Because Chip asked a question about, could we do this with solid state? I would say no. You cannot do the Montauk project and the Philadelphia experiment with electronics that are solid state. They just can't take the voltage. That's the problem with solid state stuff. So sometimes tubes, see how there's a six, oh,
Oh, yeah, gone.
see it says 3AL5, 6AL5, and 12AL5. So basically that's the same tube, except they've set it up to run at 3 volts, 5 volts, and 12 volts, essentially. So there's different models, but it's still the same kind of tube, essentially.
Historic question. When they chose these codes, AL, did they have a word in mind when they came up with these initials like AL? Did they have something in mind? A stood for this and L stood for
I,
that,
I,
or
I
it was
don't think
random?
so. What do you guys think, Alan and Paul?
Well, in the original numbers, then they changed their formatting over the years, but when you see those 5 and AL, 6AL, and 12AL, usually the first number is the voltage that the filament runs at. And then they kind of picked arbitrary numbers to differentiate one manufacturer from another. So it was more like RCA made the AL and Westinghouse made the GD or something like that. So,
Yeah. And,
but it might have meant something to the people that gave it the name, but I don't know.
yeah, and there's a lot of different tube numbers, and there are different systems, like Paul said. So the earlier
I can
ones,
quickly look that up if you like. I can
no,
quickly look
no,
it up.
no, no, it's okay. So the earlier ones are like 845s and stuff. They're just numbers, and
Numbers.
that was like in the 30s. Probably started in the 30s and into the 40s, and then they ran out of numbers basically, so they started using the alphabet to designate things. So I think it's yeah, probably more random than not. What do we? Okay, is so this is the 845, which is the tube that I've talked about a few times. This is the most linear audio tube that there is in existence, except for there's a big brother of this, essentially, which we're going to look at in a second. Now, the 845, when I operate mine, I operate them at 1,000 volts DC on the plate and about 75, maybe 65 to 75 milliamps of bias current. They This is the magic, and my understanding is Nikola Tesla himself developed this tube. It came out in 1940, and he retired from RCA in 1939. So I'm pretty sure he had his hands on this one. And so this one operates at 10 volts for a filament, so it's a little bit higher. Um, and the amplification factor is 5.3. So that is they call it the mu 5.3 the amplification factor. So triodes generally like this have a low amplification factor, but they're much, much, much more linear than some of the other ones that have higher, like pentodes. I don't know how high it goes, but pentodes can have a much higher amplification factor. And that's basically just talking about the voltage gain. So if you've got, in this case, if you've got 1 volt coming in, AC coming in, and it goes through this tube, on the outside, on the output, it'll produce 5.3 times 1 essentially, right? Or whatever voltage is that kind of thing. And we'll look more about if you keep going a little bit, Brandon, we'll look more at the operating specifications.
Yeah, I had a question on the amplification factor. Is that actual power? It's actually going to amplify 5x more power compared to the signal that you put in. Is that
Yeah, voltage
if I re
potential. Yeah.
so it'd be more than just voltage. It's voltage times current.
Well,
for
yeah,
power.
yeah, there's current in there as well, but if you think about it, so let's say it's 5.3 and you put 10 volts in, now you're going to get 53 volts out the other side with an increase in current for sure too, yeah. So the power does get increased as well. So the next thing, Brandon, here, is just, okay, stop, yeah, oh, stop right there. So this is actually the most important part. This is single-ended Class A operation. You can operate tubes with different classes, like you can go Class A B, or you can go Class B, or you can go Class C. And we'll talk about all of that at some point. So the operation that I use is actually in the middle of these. It's the one that says 10 volts on the filament, 1,000 volts on the plate, and then um, I'll talk about that DC grid voltage in a second because that's actually the magic of the tube. But I do want to go down and show you the 9,000 ohms of resistance. That's the load resistance. So that's the setup that I use. And with one tube operated like that, you can get 21 watts of output with 5% distortion. So what we want to really talk about here is how the tube actually works and how it gets turned on. And the big part of this is the DC grid voltage and the peak AF grid voltage. And you notice that the DC grid voltage is negative. So what we do to make the tube operate is we actually turn it on, and in a Class A operation, we actually turn it on at half throttle. It needs to operate at half throttle, basically. So this specification would be, okay, 1,000 volts and 65 milliamps on the plate current, but it's a negative voltage with the bias circuit, and that's the negative voltage is part of the secret of all of this. We also have to remember that in a vacuum tube, because there's vacuum in there, there's a permittivity, I might be saying that wrong,
Permittivity.
permittivity change in things. And if you guys want to talk a little bit more about that and how it sort of affects the tube and the operation and whatnot.
Yeah, especially if it's a plasma tube, right? Because permittivity has to do with polarization of the medium. And so when you have plasma, you're going to have a much greater polarization. And so
So
that's why asking what the gas is related to that.
yeah, well, these don't have gas in them. These are vacuumed down to a very, very high level. I don't know exactly, like 9 or 10 Thor, I think it's called Tor. Um,
Mm-hmm.
the thing about it is that what you have to do is you have to turn the tube on to get stuff working, and then at half throttle. And then basically what happens is that the music flows through and it operates, and from that basically it goes back and forth to its operating point where it goes to well, not full cutoff, but if you operate it correctly, and we'll see in a second here in the tube drawings. So let's go a little bit more. Now
I,
see, let's
I did
stop
have a
there.
question
Okay.
because you mentioned Class A, B, and C. Real quick, what kind of does that mean when you
Yeah.
talk about the class?
Yes. Yeah. So that's great, Marie. Like that's why we stopped it right here. So we just looked at single-ended Class A operation, which actually means that the tube is turned on the whole time, and it's turned on halfway, essentially. Now, most amplifiers, or actually most amplifiers we used to build back in the day, would have the tubes turned on with their bias current, and it would be about 10% of the power that they operate. So let's say it's a 100-watt amplifier, the bias current is going to be about 10 watts. So when the music flows through there, that 10 watts is still operating in Class A, but the B part is when the tube actually shuts off, and then it has to come turn itself back on again. That's why they call it Class A and Class A B. Now, if you want real fidelity, you need to operate in Class A. Class A, B is like a compromise, essentially. Yeah.
And what's Class C?
Class C is uh, it's used for zero bias transmitters and stuff, and maybe you guys can jump in on
Yeah,
that
you
one.
go even further down the curve, like if you got a picture of the curve. So these curves are sideways a little bit different, but
Yeah.
picture,
Can you
if,
rotate that one, Brandon,
yeah.
by
Sorry,
chance?
sorry,
So,
sorry. What
well,
was
yeah,
that?
if you imagine that on its side and you're looking at that curve, your signal coming in, well, if it's
Let's
oriented this way, we could do it this way. So the
well,
signal coming in would come in from the side. And if it's Class A, it's going to meet in the middle of that curve, and your plus and minus will go up and down. And then Class B is shifted down to the bottom of the curve, so it's partially off. And Class C shifts it right over, so it only comes on part time. So it only
yeah,
pulses
it's more
a
like radar,
little bit
essentially.
of the curve. Yeah.
Yeah. Brandon, could you twist that thing so that we can make it go this way?
Let me see if I can do that.
Ro-
Let me see if I can do
ro-
that.
It's at
Because
at the bottom. There's
Rotate.
a rotate
Yeah.
symbol at the bottom of your picture.
Yeah, yeah. No, no, not that one. I'm looking for because it's a PNG file.
okay, yeah.
Um, right,
Once
so
we get that twisted, I'll talk a little bit more like what Paul was saying. We'll show you the bias point where the tube is essentially set to turn on in a Class A operation, and then we'll show you how it goes from zero or from that point to zero and then back again. And that's
I'm not sure.
basically
I'm not sure if I can do it on this thing. I might have to put it into if I put it into a paint program. I could rotate it if you want.
yeah, because
I think it
this
came up.
That's
Yeah, right
At
at the
this,
the
bottom. Yeah, if
at
you
the
see it,
bottom, you have a rotation button.
yeah,
To
if you
rotate
click
it
on it,
left.
there is a rotate.
no.
Yeah,
At the
This is
bottom
just
of your
underneath,
picture.
down, keep
yeah, yeah.
going
I
down.
Underneath, go
see it.
lower.
Yeah, I see it.
Yeah.
There,
I
there
see
you go.
See. Okay, so
there we
That's
go. That's what we wanted. So just show the whole thing of where the lines are. You have to shift it over.
shit, I can't. It doesn't go anymore. It doesn't go
Oh,
anymore.
it's cut off there.
Okay, well maybe let's look at the next slide. Maybe the next slide has got the whole thing in it. There it is.
Oh,
So
yeah.
you want to go to the graph? Is that right?
That's
Yeah.
what we're looking for right there. Okay, so on the graph here, if you go up from 1,000 volts and you find 65 milliamps, so you've got 50 milliamps, 100 milliamps. If you do the divisions to figure out what 65 is on the side there, which is probably going to be like one, let's see here, 75. It's probably like one of those or two squares up from 50, maybe three squares up from 50. And then you go down and look at the 1,000 volts. So what you got to do is come across with 65, come up with 1,000, and where they meet is going to be your bias point.
so at
And
1200 and
in this case, it's between
14.
minus 150 volts and minus 200 volts. That's basically where the bias point is, and that actually talks to the AF grid swing that we were looking at earlier. So the tube will start at that the tube is set at that point essentially, and it's operating at half throttle. The tube is halfway open and it's already doing its thing at halfway. And then when the music comes in, then the tube will go, and make sure I'm doing this correctly, Paul. The tube will go from that point down to zero, and then back up past the bias point in equal voltage back and forth from the bias point, right, Paul?
Yeah, it wouldn't go right to zero though. Like if you're Class A, you're going to be in the middle of the curve, so you guys
Yeah,
are going to go up and down this way. So in the milliamps that it's sending out through the plate.
yeah. So if it swings, okay, the real way that you actually do this is you usually set it at half throttle and half the current. So if it's set at 100 or 65 milliamps, then double that is 130, right? So that's basically where it'll swing back and forth. And I don't know that I have a slide that actually shows the bias point and how it moves back and forth. The other thing that's really important here is see how the lines at the beginning are of 0 and minus 50, minus 100, minus 150, minus 200 are quite straight. They're the same spacing apart, and they're very
Spacing.
straight, right? As you get down to minus 250, 300, 350, and all that, you can see it starting to curve. So now you're losing the linearity, essentially, right, guys?
Mhm.
Yeah, yeah, that's where you want to have for your best sound in your amplifier, you want to keep everything within the range of that equal spacing. Then it's a totally linear tube. So you won't hear any differences in amplitude between your lower frequencies and higher frequencies. It's totally bang on
Yeah,
true reproduction of what you're putting in. Yeah.
yeah, yeah, exactly. So that's the 845. And again, this is and I've got amplifiers. I actually designed an amplifier that uses two of these in parallel in a monoblock, and you get about 32 watts of single-ended Class A out of it.
Wow.
I've also got monoblocks that just have one tube, and I get about 20 watts of single-ended Class A out of those ones. Yeah, it's a beautiful sounding tube. I've listened to almost all of them, and this is the best one.
Have
Yeah.
you heard the Komoro 845?
You know what? I've got a whole bunch of different ones.
Mm.
Like you mean tube brand or the actual amplifier?
Well, that was the designer. I worked with him.
What Komoro?
Yeah,
So explain more. Is it like a single-ended setup, or is it
yeah,
just
yeah. That's a right. It was like basically it was a direct coupled, 3-stage direct coupled.
oh, nice. Wow.
Yeah, very
That's
much so.
that's hard to
Yeah.
do. That's
Yes,
really
it
hard
is.
to do.
Very high voltage, and really good custom, obviously,
So what was
output
the
transformers.
input and driver stage tubes would have been for that? Do you remember?
I think we had well, the usual suspects. I think we had a 6SN7 in there.
I was going to say that for the input, yeah, and then
Mm-hmm.
yeah, and then something else to drive it. You can drive it from there too, depending on what kind of circuits you have and stuff too, right?
Yeah, yeah, yeah. But
Yeah,
I think one of the key reasons for it sounding so good, and it enjoyed a lot of popular opinion, was the high voltage. But it was high voltage circuit,
yeah,
higher than usual. The
and
high
direct
end that you mentioned before.
and direct coupled. Like direct coupling. So
Yeah.
normally when we couple between stages, we use a capacitor. For the
Mm-hmm.
most part, there are other ways of doing it. And capacitor, anytime you put a capacitor into the circuit, you're changing the sound, no matter what you do. And
Mm-hmm.
there are better capacitors. Your best capacitors are actually Mondorf, if I'm saying that correctly, from Germany. And
Yeah.
their silver gold ones are literally the best of the best. And
Mm-hmm.
they all do sound differently because I've listened to lots and lots and lots of them, right? And have my sort of favorites. So when you direct couple, you get rid of that coupling capacitor is what it's called. But now you have to make sure that all your voltages and everything are like dead on. So the power supply part is the magic. But what I've learned about tube designs is the magic is always in the power supply. You pick a really linear tube to start out with like this, but if you can build a power supply that has like I was saying before, a full wave bridge with 4 tubes, now you're into the best of the best kind of thing, actually. And that was one of the amplifiers that I designed, the OTL that doesn't have an output transformer. I use bridges for that one. Yeah,
Mm.
for all the circuits too, actually. There's 3 different bridges in it. I think I even built a bridge for the DC, like for the heaters and stuff, if I'm not
So
mistaken.
is that what the
Or
bridge is
something.
for, is to rectify to DC?
Yeah,
And so the most stable DC, and you have control of that, that allows you now to engineer everything.
yeah,
That's why you say
exactly.
the power supply is so important, is because you're trying to make a very precise DC that you're in control of.
Yeah,
Wow.
yeah, exactly. And there's another. I didn't include it in this one, but I did build a stereo that uses car audio, and then I run it with a DC battery. So now you've actually already got DC, and I ran that setup so that it was tri-amplified. There was a separate amplifier for the tweeter, for the mid-range, and for the subwoofers, and and then it was all ran in Class A, and that little setup sounds fantastic. It produces sound like in the $25,000 range, kind of if you were going to go buy a home stereo sort of thing, right? So don't ever car audio, because it runs on DC, can be really awesome. I used Alpine and some really good amplifiers in that. Yeah, so let's keep going.
Can I ask you, Maury, can I ask you a question? Did you work as an electrical engineer when you were working? Or-
Actually not. It's a I was in essentially computer science and programming, but back in the day, we're talking 60s, right? There, if you wanted to do anything with computers, that's electrical engineering.
yeah,
And boy, I lucked into it because that gave me the background in fields and everything else that came to home to roost in the 70s when I learned about the whole ZPE thing. I had the background of the physics that allowed me to dive into that. So I was quite lucky, right? That I was forced into electrical engineering, kicking and screaming. And so my strength was I was good at the math and all that, but I was not good in the lab with the other. I admired my colleagues; they were really good. And I said, well, when it comes time to building the stuff, we'll defer to them. And I can think of the ideas and what to build, but I was pretty sloppy as a builder, right? So different skills, right?
yeah,
That was essentially my background, and I had a genius colleague that I worked with hiring at Dave Faust, who was all part of the team. Everybody looked up to him for the building and what to get. And the real irony of his career was he wasn't good at math, so he really never got an electrical engineering degree.
oh
He
wow.
was just being assistants to the professors and things like that. And then boy, he was the lead guy when it came to assembling hardware for doing the various experiments. Everyone deferred to him. So it's a real irony. He was a true genius. And I said, well, he'll do the building and I'll do the thinking, right?
That's
And
awesome.
that's why I would say, oh, that's hardware. You take care of that, right?
That's awesome.
Not my problem.
So now we have, can you back a note again a little bit, Brendan, so we can see the whole thing? So a Western Electric tubes basically are the best sounding tubes that there are, essentially. The 300B Western Electric, I think there's more single-ended amplifiers built with that tube than there is in any tube in the world, period. Although I like these high voltage tubes better, these transmitters, and this one, the 212, this is the big brother to the 845. And there were years when they didn't have these anymore because they weren't making them again. But then they started making them again, and now there's quite a few amplifiers, very, very high-end amplifiers that do use this tube.
Yeah.
So you can basically get more power out of it single-ended, right? Yeah. What do you guys think of the 212? Have you seen it before, both of you?
Oh, yeah, sure. Yeah, I'm very familiar with it. By the way, the 845 and the 212 are, they're roughly about 8 inches high. These are big
Big
tubes.
tubes,
Yeah,
yeah.
this one's actually, I think, 12, and it's about that round. The 845 is about 8 inches tall, and the bigger ones that I have are about 3 inches in diameter. This one's like a lot bigger.
And
It's
what
it's
is actually a vacuum tube doing? Is it taking the place of a transistor? What is it? Is it doing a similar task to a transistor? Vacuum
yeah,
tube.
but
Right.
much more linear.
So so a vacuum, so a transistor amplifies signal. One of the things it does is it's a switch. So at a certain switch, it amplifies the signal. Is that right? Transistor.
Mm-hmm.
Yeah.
Yeah.
It's like a valve. It's a valve. It's a gate. You know,
Yeah.
that's why they're called valves. Yeah.
Alan, that's beautiful because in fact they are called thermionic valves.
Right.
Right? That's that proper name. And so the thermionic part is because they're a hot cathode, essentially, you get electrons flowing. But yeah, they're definitely a valve. And so the valve is, there's a bit of, well, we'll go into that a little bit more because there
So
is a circuit.
transistor basically, doesn't allow it switch at a certain voltage, a certain current voltage. It switches and amplifies the signal. Otherwise, it doesn't let that signal go through. So, like saying a gate. So
Yeah.
that's what
Well,
they
it's a
you remember the
variable
phone.
valve.
Yeah, it's a variable valve. Yeah, exactly. They both do the same thing. Remember that tubes came before transistors, and they both do the same thing, but tubes do it much, much, much more better for linearity. And when you talk about audio, that's what you're after. Now, in solid state, you do have things like avalanche that occurs that can be very helpful, maybe in free energy and some other aspects of things. But as we're talking about, looking at charge clusters and whatnot,
It's
there
basically
there are
it's basically the vacuum tubes and the transistors that made computers possible. That's the main
yeah,
part of a computer, isn't it?
and the Philadelphia
Logic,
experiment.
logic gates. Yeah.
Yeah.
We're talking about the Philadelphia experiment. They didn't use these exact tubes, but that's what they had used tubes, right? Yeah. There is a we'll go into it a little bit later, but there is a type of tube um, that is used for radar that clusters up charge clusters by its geometry built inside, right? I don't think I've included it this time, but next time we can look. So there you go, 13 and 5/8 long and 3.5 inches in diameter. And I think the newer ones might even be a little bit bigger so that they can control the heat or the heat is, and there's more vacuum in them too. That's the other thing that's kind of important. Yeah. And see how it says, Brandon, if you could just stop for a sec. Uh, may be used as an audio frequency amplifier, which is what I'm talking about, but it can also be used as a modulator or as a radio frequency oscillator or amplifier. So do you guys want to talk a little bit more about that?
Basically, it's just a matter of frequency. If you're in the audio frequency range, then you're going to be running, from 10 hertz up to 20 kilohertz or 40 kilohertz.
Yeah.
So that's considered the audio range. And then when you go above that, then you start getting into higher frequencies where there'll be radio frequencies, and they'll actually radiate from an antenna and send a signal through the air. So it's a
And
matter of how fast it's switching on and off, really.
and so when it's a modulator, what are we doing there? Because that's a bit different than just amplifying
Well,
your audio,
you'd
right?
make it, yeah, it'd be an oscillator. So when you make a circuit that makes that tube oscillate at a single frequency, that would be your transmitting frequency. So you basically have there's different types of oscillators, but it's a circuit that you build that just puts the tube into resonance where it just starts going nonstop. And it'll stay really fixed to that. Later, they started using crystals to keep it locked on, and then that moved into solid state. But they'll oscillate really well on their own, and then you can tap into the modulate. So the first transmitters were called continuous wave. So it was just always modulating, and then you'd send Morse code just by putting a noise on the line, beep, 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 beep. So you're shorting out the cathode basically, and
Okay.
that's how they do the first transmissions.
Very
And
cool.
then the tube evolved into getting the grids and the plates where you could modulate on audio. So you have audio pre-staged where you generate your audio frequencies. Then you put it into onto the one of the grids on the transmitting tube, and then you're sending sound through the airwaves.
Yeah. Yeah. Very cool. And I think so. A couple of things that you said. First, it resonates. The resonance is very, very important in free energy and everything that we talk about too, right?
Yeah.
Yeah.
So
Um,
that's kind of like the history of the tube. The modulation changed the amplitude, and
Yeah.
that just means I'm changing the amplitude of this carrier thing going on, and so you're modulating at at the sound frequencies way down in the kilohertz range, and to change what it sounds like, and the carrier was way up, depending what band you're in. And then it evolved to frequency modulation, where the signal was basically shifting the frequency itself
Yeah.
to encode it. And then the receivers had to decode that to get back to the sound that you're the sound information that you're getting to. So it's kind of evolving the history of it.
mhm.
So first radios were amplitude modulation. That's
AM, yeah.
yeah, how we learned to do it. In the original crystal radios, you didn't need any power supply for a receiver
Yeah.
because there was enough
Yeah.
power on the signal itself. You could directly receive it and rectify it, and it didn't take much in the way of circuitry to listen. So
Yeah.
it's kind of cool the way that evolved.
Yeah.
And that was the roots of T. Henry Moray. He just loved crystal radio stuff.
And
And
so
and
this is an interesting thing because I think it was Paul that or John Hutchison. Remember we were having that conversation about those pink crystals that were in those
Yeah.
tubes?
Yeah.
And
Yeah. I
so
didn't
that,
get a chance to look it up, but that's what I was.
okay, well next time let's
Yeah.
figure that one
I'll
out
show
because
a picture of the mystery crystals and yeah.
exactly and find out what tube, did it say what tube type it was in that picture?
Yeah, I think it did in the picture, but I didn't dig into the manual to
Okay,
read.
I'll have a look at it too, and then we can maybe next time we can go through that a little bit more because that's a golden nugget,
And
big
so with
time.
that T. Henry Morey and the tubes and free energy kind of concept too, it's also, I don't know if you've seen Rossi's, Andrea Rossi's newest patent, but he patented a vacuum tube energy capture system, which it
Mhm.
sounds like he just basically ripped off from the Russians because the Russians kind of came out the other day and said, "Oh yes, that's one of the experiments we gave up on a long time ago." So yeah, it's kind of funny.
He's raising the investment capital right now.
What
Yeah,
is that?
yeah,
Paul, was that Rossi's ECAT comeback?
yeah. It's his latest
Yep,
thing. Yeah,
I
yeah,
did see that actually. Yeah, yeah.
yeah.
So
Um,
was his stuff a complete bust earlier, or did he at least have some working experiments? Right, as people were getting excited and
Yeah,
investing in his,
Yeah,
so
did he have
many
and
something
promises. Yeah,
right?
over the
the bugs
years.
weren't worked out.
Yeah,
So
okay.
he had a phenomena, so he wasn't a
hmm.
complete fraud as far as
Oh yeah, there was
that.
something.
And then I could see that then marketing takes over and exaggerates. I know how that works.
Yeah.
In his own mind, right? He's the marketeer as well. So
Hmm.
usually different people are doing it, and the inventors are pulling out their hair. No, no, you can't say that.
So this is showing the some of the operating parameters, and this tube actually operates at 14 volts DC on the filament, and it requires a lot of current to operate it. 6 amps of current is a lot. The thing here too that I'm reading is average characteristics at 2000 volts. That's the thing about this tube too. It runs at a lot higher voltage. Um, 2000 volts direct plate potential and minus 90 volts grid bias. So I think there is a chart that we'll try and have a look at in a second here. With that given operation, the tube amplification factor is 16. So it's not quite 3 times as much as the 845, but it is considerably higher, which makes it a better candidate kind of. The DC plate resistance is about 1900 ohms, which is fairly low because it's got such a huge plate. Um, what else we got? Propeller operations. So there's a different operation with a plate voltage of 1500 and a grid of minus 60, the filament at 14. Then you get different amounts of current out of it, essentially, different cases it's showing. The maximum operating voltage on this tube is 3,000 volts. It has a maximum direct current of 350 milliamps, which is a lot. Like that's why this is the king, right? Yeah. The maximum plate dissipation is 275 watts. Now what is that? That is basically the voltage times the current that you're actually setting the bias to. So that means that this tube can be operated a lot harder, if you want to say it that, or yeah, right? What do you have any input on that, you guys?
It's a big valve. When you turn the valve, it opens really wide.
Yeah, there you go. Perfect. Yeah, and
most of your energy to drive it is a heater. It's just the filament to get those electrons boiling.
yeah, boiling is a good way to describe it because that's exactly what happens. They get boiled off the cathode.
Yeah.
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 Absolutely. Especially when I operate them. I typically operate them a lot harder than you're supposed to. And that's why I blew up one of my 845 monoblocks. The output tube let go, and then it destroyed a whole bunch of stuff in its path, essentially, right? So I've got to fix it. But that's how you learn, though, also, right? So there's a Class A operation, single-ended at 1500 volts, minus 57 volts at the grid bias. You have a direct current of 170 milliamps of idle current. That's insane. Most tubes don't even, well, maybe the 845 at full operation has 170 milliamps. The plate dissipation, again, is the overall bias setup, the way that you set it up. And in this case, 5,000 load impedance. So Paul was talking about output transformers. Now you have this tube or the 845, the output tube connected to an output transformer, which actually these tubes are quite high impedance. So that high impedance has to be changed to a low impedance for the speakers, essentially, and it's doing its job. And the output transformer is probably the most critical key of the sound of a good amplifier, other than the power supply part. They're really, really critical.
So Ed, how did you manage a output transformerless?
Okay, that's a great question. And I'll bring up those 7240 next time. We'll talk a bit more about it, but that's a great question. So this tube right here has a plate, or like the load is about 5,000. Where's the plate impedance? Could you go back the other direction, Brandon, to the beginning of just this one, and let's see if there's a plate impedance, because it's got to do with the plate impedance. You have the plate impedance of the tube that I chose is only 67 ohms, right? Where this one is it was there.
1900.
Plate, where is it?
Plate resistance 1900 ohms, right?
That's the same as if it's the resistance is the same as the impedance under certain circumstances.
Yeah.
Yeah.
I always say look at resistance as picture in DC and impedance picture AC.
Yeah, exactly.
Inductive reactance and capacitive reactance and resistance.
And then it's all frequency dependent when you get into impedance. So
yeah, exactly. Yeah.
I had a question on vocabulary. We're talking about plates. Well, we have a plate where the electrons are boiling off, and then we have the receiving plate on the other side where they strike. Did I call both of them plates?
No,
that's my question.
The anode is the one that they boil off of, and then the plate, and then the plate is the one that receives it, and then you're going to see here in a second that there's a grid in between there as well. As a
I understand. They changed the vocabulary when they got the transistor vocabulary. They call it the emitter. Okay, so when they in tube vocabulary, the plate they're only referring to the receiving, the anode side.
Yeah,
and the cathode they don't talk when they say plate. That's what they mean. And if they want to refer to the emitting side, they would just say cathode, and everybody
generally,
Okay, that's how they make the distinction. Okay, and the grid, of course, is the controller. And
Yep.
okay,
Yep.
got it. Thank you.
Exactly. Yep. Yep. Cool. Yep. So where were we? We've gone
We're
through
down,
this.
we're down here.
Yeah.
Um,
So okay, so with 1500 volts minus 57 as the bias voltage, and again, that's super important to understand that when you bias a tube, you have to use negative voltage. Negative voltage is the key to free energy in some ways when you start thinking about it. Um, but in this case, you get 50 watts of single-ended power out of one tube, which is about double what you can get out of an 845 essentially. So that's what makes this tube the king, essentially. Yeah. And keep going here. We'll see so there's a class B operation for balanced two-tube circuit. The setup is quite different. There's a lot less current flowing on the bias setup, and all the parameters change essentially. The grid voltage is different again. It's a lot lower, negatively lower essentially. And then if we keep going, Brandon, we'll show the that shows the class B radio frequency.
thanks, sorry.
Are these tubes fairly expensive, Eddie? Do you know?
They are very expensive.
These are
I
probably
I would
rare.
say several $1,000s each, probably.
Wow.
Yeah, and if you were to try and find a real Western Electric, like new old stock one,
Right.
I've seen a pair of 845 new old stock tubes that I wanted to buy that were from World War II, which are like the best ones. That was $10,000 US. Um,
Oh.
a pair of these is probably could be even 100,000 probably. Um, yeah.
That
So
means,
You know,
yes,
Western Electric is still in business. You know, they're making high end amplifiers now.
You're making them again, yeah.
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 Are they making the 845? Because I know that other guys are doing it, but or I'm sorry, the 212. I
I
mean,
know they're doing the 300B, but
yeah,
Right. Yeah.
yeah.
yeah. They need to build this tube again.
Hmm.
Western
Well,
Electric.
right now it's a collector item, right?
Yeah,
You save it for an investment.
yeah.
invest,
I've
yeah,
I've got a collection of tubes that is worth large. Yeah, definitely. Yeah. You have, but it's not that you have to use them. You have to have spares when you start building this stuff. Because they're like light bulbs. They do have a specific length of time in operation.
because
Class.
computers were made from vacuum tubes early on. So does that mean the
Mhm.
computers were very expensive because of the tubes were expensive?
Well, in relative thinking, probably yes, compared to putting on a chip, like on a silicone chip. Mind you, the chips cost a lot of money to produce too, so it's hard to say exactly,
Do you know?
right?
Do you know if Alan Turing used vacuum tubes when he built the first
Oh
computer?
yeah, had
Used
to.
vacuum tubes.
Oh
Yeah.
yeah, there were no transistors back then that we know of.
Yeah, exactly. There were kind of, but they were just experiment. The Germans were experimenting with transistors, like even into the 30s and stuff. Actually, when they say that it came out of Roswell, that's not quite true. Sorry, guys. I'm just sorry, but it's
Well,
not.
In
well,
the in the
it
in the
came out
middle.
of Crystal Radio hobbyists. The
Yes.
variety of things that people would try with the point contact
Yep.
on the different materials
You're
was
Mhm.
absolutely
wide
right.
open. So the hobbyists were really where the inventing was being done. That's why Moray had
Yep.
exotic contact stuff using radioactive material to get his plasma going.
Yep.
Right, that was the key to his stuff. He didn't have to provide any energy at all to get the plasma going. He's using typically radium, salts of radium,
Okay.
and
Um,
the critical clue is they're alpha emitters. And so, if you want to work with plasma that's where you're oscillating the heavy particles, and T. Henry Morey says that's the key to device, and that answers Chip's
wow.
More,
question:
more,
what's the
more,
clutch? is oscillating the ions in the
Yeah.
plasma and try to work at that oscillating QSMR. That was the clutch or the grabber of activating the vacuum.
So
What's,
Moray,
what's important about the what's important about the plasma in all of this?
The plasma, what's important about the ions in the plasma? Most of our plasma work focuses on the electrons and their behavior in the plasma, which is way higher frequency. The ions are down in the kilohertz region on where their resonant frequency. But to answer your question, what's important about them, it wasn't really known until quantum electrodynamics came along, where it's night and day the way they interact with the vacuum. And the quantum vacuum, the ions have steep lines of convergence in the polarization of the vacuum onto the particle itself. It's kind of centralized, where the electrons smear out.
yeah,
The actual quantum description of the vacuum polarization, which is the interaction between the particle and the vacuum energy. Right? And it's that interaction. That's the big discovery when the quantum vacuum. It explained why the ions were so important. Morey just discovered it, right, empirically as he was
yeah,
working with his experiments. The whole quantum vacuum stuff never came along till the 30s. Well, Morey's working back in the late teens, the 20s. He's working in that time frame, getting that energy machine demonstrated.
and
So he just knew that that was the important principle, but the why didn't come along until we brought the ether back in the
yeah,
form. He just says I'm activating the ether, right? But we had to bring the ether back uh, into the quantum vacuum, which is the quantum foam. They used to have a liquid uh, model for the ether. It was hydrodynamics was their description of the ether. It flipped over when the quantum vacuum was discovered to the quantum foam. It's like a turbulent plasma all the time.
yeah,
And that quantum vacuum was, you talk about the most powerful ether model you could pick. That was it. Not to mention self-organization and all the things that can come out of a turbulent plasma in a nonlinear system, and the
yeah,
foundation of that is power production. Right, it's
yeah,
right there in all the
and
theories.
and
Everything fit together, but the importance of the ions. Morey stressed that, and of
yeah.
course, I had to stress it too. I didn't have a choice.
So, what's interesting about what you just said there is you were talking about the alpha particles oscillating. Well, John Hutchison recently showed us his alpha and beta canon, essentially, that he used to do, I think, the best Hutchison effect ever. And you can watch it and you can hear it. You can hear that he's got that thing turned up from previous times. Essentially, he had a file that bent. He had a file that broke. He had some aluminum that broke. The table shook. There was something that flew off the table. Another thing came from nowhere and sort of ended up in the zone. I highly recommend go checking that out. And they're all on my playlist on my Technology Envoy channel. Yeah, crazy.
Going where angels fear the tread. His experiments, and he's operating intuitively. This is just coming to him, right?
Yeah,
That's the most amazing
Yeah.
thing. There is no why did you do that? Oh, I don't know. Twiddle this, twiddle
yeah,
that. It just
I,
worked. And so,
yeah,
but I think it's all understood. And Judy Wood, does that name ring a bell
yeah.
regarding
Oh
the
yeah,
Twin Towers and all that?
definitely. Yeah,
Sure things. Oh, we have this developed in our classified
absolutely.
programs, and we can make these weapons out of this.
Yeah,
And the key may simply be that, oh yeah, you start working with the ions and the plasma, we're really creating coherent energy effects in the vacuum energy, aka ether itself.
yeah,
And there's your clutch as they work with
Yeah.
it.
yeah.
And
And
if
that
it could,
coherence.
yeah,
Yeah,
well, right, because
yeah,
now they're training the vacuum to follow the ions,
yeah, yeah,
right? And
exactly.
so and probably you'll get your warping space time in your gravity effect, and just doing experiments with mercury vapor and a caduceus piping system. You
Yeah,
see that on Vimana simulation, and they're
Yeah.
making those things take off. If you dangerous experiments, because it's all sealed up. If that explodes,
Yeah.
you're
Yeah.
gonna be killed by the mercury vapor.
Contamination is,
Oh yeah,
yeah.
you don't want to experiment with that. But it could be that simple, and that's what that anti-gravity group was experimenting with. And I said, boy, that's so dangerous. But nonetheless, they would show some videos of their experiments to go out in the woods. I'm sure it's completely illegal. You're
Well,
poisoning
that, yeah,
everything in that
that's,
place.
yeah, that's
Uh,
a good point.
anyway, the whole point of mentioning that is it could be that easy. That's what kept coming to my mind. It could be that easy, but people are not focused on it, mainly because the vacuum energy and the whole ZPE thing is not in their awareness.
Yeah.
I was just amazed. Electrical engineers, professors, none of them heard of it. And yet there it was in our library, just
And,
a fragmented science historically. I said, whoa, you're missing the best stuff.
and
And it's right there in our library.
you just mentioned ZPE, which stands for zero point energy, and we know that Ken Shoulders was the man that coined that term, right?
Actually,
So,
it was coined back at the beginning of quantum electrodynamics.
okay,
Somebody said on the wiki, I coined it. It was not even close. That was the 0 point means what happens at absolute zero. That's where it came from. And what's the nature of the fabric of space if we remove all light, all heat,
yeah,
everything, 0 degrees Kelvin, right?
yeah,
0 point.
exactly, yeah,
That's all. That's all the vocabulary referred to. And then the answer was in quantum electrodynamics. There's all this fluctuating activity, like microscopic electricity, microscopic lightning occurring in the fabric of space itself.
yeah.
So that's where the word came from, right at the beginning of quantum mechanics. What's
And
this
when,
underlying fluctuation that causes the uncertainty principle,
and
right? Heisenberg,
when,
etc.
what year was that, Murray? The you talk-
1930.
okay, yeah,
1930. It's such a small boy. We eliminate the vacuum ether 1905 when relativity gets accepted. Scientific community jumped on board and removed the ether, and then the ether doesn't exist. 1905 when special relativity, because it's so much easier to do calculations if you just don't have one, right? You
yeah,
just pretend space-time's rubbery and I can get the same calculations. And then in 1930, it came back with quantum electrodynamics, way more powerful model for the ether and Wheeler derived it in the 50s as the quantum foam model and
yeah,
things like that.
yeah.
He had the orthogonal flux model. Other people kicked it around in the old ether theories, higher dimensions and those ideas, but not that. So we're talking, this is what amazes me. There's a 25-year gap in science where the ether's rejected, thrown
Yeah.
away in 1905. And that's amazing how they come to throw away common sense and accept
Mm.
relativity. But the
Yep.
reason for that is a very compelling reason. And then in
Well,
1930, it came back as when the quantum theory became recognized as having to exist, and the 0 point energy was recognized in the foundation of quantum electrodynamics. And if you do not have that in there, you don't even come close to predicting the stuff that's going on in quantum electrodynamics, which was considered the
Yeah.
perfect theory, the blah blah blah. And I said, wow, what dominates the thinking of the majority of human beings on the planet and the majority of scientists
Yeah.
in all of academia, because they're not physicists, they never are taught of this historical development coming in quantum electrodynamics that brought the ether back.
Yeah.
They're just taught it doesn't exist. And the
That's
electrical engineers were all the same way. I said, man, you guys can do stuff, especially teaming up. I'm thinking of my hardware friends, right?
yeah.
And says, you just got to know it exists, right?
Yeah.
You just need
Yeah.
to experiment. And I was just amazed at how so few people know
What,
any
yeah,
of this. And this
what,
is just standard history of science.
you have to go back to the 1904 theory of relativity. It was a year later that Einstein made it special, mainly
Right.
by getting rid of the
Right,
ether.
right.
Yeah.
Lorenz
That's,
did it.
yeah.
Yeah,
Poincaré.
what
Poincaré, yeah.
was it? I asked this question. Very few people know the answer, but it's obvious. It was in the textbook. What was so compelling that would make the scientific community, the physics community, give up on common sense notion of space and time that
Michelson and
everybody
Morley, it was the Michelson and
experiences?
Morley experiment. Michelson and Morley.
Right.
Yeah.
The
Psychotronic
ether.
warfare.
And then what made them so willing to give up the ether? And more impressive, accept this crazy notion that space-time's rubbery, general relativity, the space warps and things like that, and your perception of what's going on. You gave up your foundation of common sense, which is the Newtonian three dimensions of space and the linear progression of
I
time,
think I think
basis of
JP
all the differential equations. And
I
I'll
think
answer the
JP Morgan had more to do with it than science.
no, that was the business. But with the science community, we're so willing to accept special relativity and give up common sense notion of space and time. What was so compelling? What unification occurred that made them willing to give it up? And I was amazed at the answer. And that it's basically unification of Maxwell's equations of the electric field and the magnetic field, right? They were separate, right?
Yeah,
One was inducing the other, but they were separate. And he says, wow, the derivation that the magnetic field is the Lorentz contraction of the electric field.
yeah, yeah.
And,
Bingo,
and here's
bingo.
and here's what blows my mind. This happens at incredibly low velocities. I thought everything in relativity, you got to be up there near the speed of light to have any of these relativistic effects kick in.
Yeah,
Not so for this unification. The drift velocity of electrons in wire at normal room temperature is incredibly slow, like 6 feet
y-
per hour. It was like an
yeah,
amazingly slow drift. There's just a lot of charges, and that's why the magnetic field is measurable. But that slow velocity in the Lorentz equations was a perfect fit, perfect calculation for unifying the electric field and the magnetic field.
yeah,
And that's more than anything else. It was the slow value v in that Lorentz equation that made that unification in Maxwell's equations. And I couldn't believe it when I did the sophomore fields. It was right there in our textbook. I went through that derivation like 3 times. It just astounded me that a relativistic effect at a tiny, tiny little velocity
yeah,
was a perfect calculation for this unification of an electric field and a magnetic field. That was the compelling reason. That unification was astounding, and in a way, I'm still astounded. When I tell the story, most people don't know the story because they didn't weren't electrical engineers or whatever. And everybody else, oh yeah, it's just a calculation. And they just move on. Everybody knows that now. Of course, we had to throw out the ether because now we unified all of this. And
So
when they don't realize, gee, a slow velocity, willing to give up common sense,
it,
really.
it's interesting that you talked about the Lorentz force because there's videos on my channel that talk about how anti-gravity is achieved essentially using the Lorentz force and magnetohydrodynamics.
Oh
And
yeah, yeah.
it's very simple actually. And that's how
Especially if you involve the heavy particles.
yeah, and that's how the hover cars are going to work. And that's interesting, Moray, because there's different versions of the hover car that I've talked to Chris about. And I think the first versions that are going to come out require some kind of charge or ions to be put in every year to replenish what's
Well,
going on.
and the Townsend Brown stuff, you need that residual ionization. I
Yeah,
think to really there's your clutch chip. It's the ions.
yeah,
That's the
exactly.
key particle. So here we
Particularly the
are.
heavy ones. Yeah, particularly the heavy
Yeah,
ones. Yeah.
Yeah,
well, whatever the protons will do. They're just so they convert that just so the lines of convergence. This is straight out of textbook, quantum electrodynamics. I got grabbed the textbook off the shelf at the library. I was showing, look, very different. I was showing the professors. So I'm teaching the engineering professors if they're willing to listen to me. I had a few that were my friends, and they were, politely saying, "Oh yeah, you're passionate, so you can do this." I said, "I'm justifying. It's all there in our science."
Yes,
So
that's
that's
awesome.
yeah. So I didn't mean to digress our tube discussion, but it's just
Yeah, let's.
amazing to me what it's not known.
Yeah,
That's not known by just common sense scientists. They have their little field memorized, but they just don't bleed over. I
yeah,
always say, well, why didn't you tell the engineers? I was getting to the physics people, right? We just might do something with it. Why do you tell us there was energy there in the vacuum? They didn't know. None of the engineers know, and they still don't know. And that's true of all science today. They don't know that this exists except for the physicist who
yeah.
just go, oh, that's just a calculation. Nobody understands it anyway, so they don't even think about it, right?
Well,
They just
maybe
don't.
I think maybe that's why we're going through this is so that those guys can watch and
Well, it's true.
understand.
Who wants to get on board? The people that
Yeah,
need to do the experiment. So our community's fine. We're even talking about it,
yeah,
but and biology, right? It's all ionic currents in biology. All biology is based on ion activation. So you're
yeah,
immersed in it, and this is how your connection to the 0 point field and everything else. It's from the ion currents
yeah,
in biology, which opens it's all just ignore because it's never taught. They the reason they don't know is because it wasn't in their textbooks during their undergraduate phase of learning physics 101 that's required to at least get
yeah.
something from science into your
Our
knowledge.
our um
And
our
anyway,
our aura basically using magnetohydrodynamics, which is a direct energy conversion from the ether. When we pulse our aura, we're actually drawing energy, and that's where the energy actually comes from for life, essentially. It's
yeah,
it's
and then
quite
as a
simple. It's just magnetohydrodynamics, and I've got a bunch of shows that I've kind of been preparing so we can go through that in a much more technical look and stuff. Yeah, so it's great that we're talking about it.
And I think when
Yeah.
we feel emotion and feel strongly, I think there's physical, lots of ion activity
Yeah.
in a coherent way
Hey,
whenever we have feelings.
Brendan, can you switch back to the live picture instead of this page here,
Yeah.
so
That's
so
fine.
we can see who's talking? Thank you.
Oh, okay. Yeah, yeah.
It's you.
That, then also that biological,
Just checking.
yeah, the biological ion relationship that shows how it can interlink with the spacecraft and supposedly these organic spacecraft that are made out of living matter that you can interact with the same way too. So you can
Yeah.
see
Yeah.
that we haven't
Um,
looked down those
Well,
doors, but that's
even spoon bending is the simplest
yeah,
example.
I'm
People start
actually,
to.
I mean, I studied metallurgy with Dr. Bruce Ball, PhD of metallurgy, but I got some information. I'm not going to say where it came from, but there's a left-handed twist type of material or metal that has consciousness built into it, that is being used and has been used for a very long time. So it's kind of what Paul said. There's the consciousness of it's of the people in the ship, especially the commander and the people that are operating the ship, is actually built into the skin of the ship or the material of the ship itself. And part of that is it's almost like like the new cars, they have a chip in them and no one can operate the car unless they've got that chip. Well, with the ship, you have to have the proper DNA. If your DNA is actually built into the ship's um, hull, if you want to call it that, although it's not like a solid. Elena says you can put your hand into them, and she's actually shown that you can put your hand in them. It's actually a living synthetic, you might say, SI, synthetic intelligence, not an artificial intelligence, but an actual synthetic intelligence. But it's got the people's DNA built right into it. And there is a left-handed twist involved with all of this that is kind of the key. And we'll talk more about that. Yeah.
Yeah, and then not to mention just amplifying technology. That's our minds can influence things right? And then you have something
Charged.
pick up the signal, and then
Yeah.
your advanced technology just amplifies it. Now you're
So
controlling it with your mind.
every time you have an intention or a thought, you're creating a charge cluster that goes into vertical time. And then as it comes to fruition, it spreads out at 90 degrees. And you know how important that orthogonal thing is with all of this. That's where our reality forms essentially. And we do form our own reality. There's no question about that. Using charge
Especially
clusters.
especially teaming up. So we've yet to scratch the surface, but what I think as a group being, a Gaia, the consciousness,
Yeah.
if we wake up, uh, become sentient as a group being, it's probably we'll have a perception that's nothing like our our three-dimensional perception. That being
Yeah.
is way more advanced. And
well, is that group being what's established, let's say, in a spoon bending party?
could
Remember,
be.
Yeah,
Could
for
be.
sure. Yeah.
I remember
Because,
Mara
oh, I
back in
remember those days, boy.
1989 in
Jack,
Sacramento,
Jack
USPA.
Hawk,
I remember
right?
you coming up to me after we had all bent our spoons and everything. You walked up to me and showed me that you had bent a knife in half, or
Well,
somehow it came apart.
wasn't me. I'll tell you what happened to me though. Is I was too much of a reductionist. When my spoon started to bend, I got scared and immediately stopped. I was a big wuss. I said, "What are you doing?" Right? They're getting scared.
They're
Right?
just
And,
charge clusters and etherons. You don't need to be scared of them.
but I did. I'll tell you a funny story because Jack Hawk was taught us how to do the party, and there were certain rules: no drinking. You got to do this or straight hours, and you're cheering, and you're really getting everybody all excited, and
Emotions. Yeah.
everybody's cheering as and you get the adrenaline up. You really get the emotions high up, and then people would start, and the spoons would start to bend, and we're making a lot of noise. We're cheering, and so we're I think we're in a dorm. I don't know what town we were in. They all mushed together, and in a university, and two cops came in to say you're disturbing everybody, you're making too much noise, right? But then I said, what's going on? They got curious. These people aren't drunk, and they're all cheering and carrying on. So they say, look, I hand a cop a spoon, right? And he goes, and he started to do it, and it bent on him, and he got all excited, and the two of them joined the party.
That's
And
awesome.
then about a half hour later, two more cops come in, right? They immediately see their colleagues and they run over. What's going on? They said, "You can't believe this." I hand them a spoon, right? And they
Yeah,
give it a try, and
Oh
then
my
they
God.
join the party. And then
That's
I
yeah.
think
awesome.
we're after midnight, right? At this point, and two more cops come in, and they immediately see the guys. They run over. The chief is livid. You guys are making too much noise. I don't care what's going on. They were trying to hand them a spoon. Said, "We're in trouble here. Stop the party." And so they finally did. That's how the party
Yeah, that
ended.
was Sacramento. Yeah.
Oh my
Was
God,
it?
that's hilarious.
It's
Wasn't it
Wow.
Andrea Puharich who started that to have the parties
Yeah, with Yuri Geller, but
with
Jack
your show?
Hawk was
Yeah.
the guy that really got it rolling. And when I was talking to him, he says, "Well, who are the best people that seem to be most talented?" And he had the answer just like that. By far, successful CEOs. Somehow
Mm.
they just know they can do it,
Huh.
right? And they can bend the big stuff, right?
Right.
Yeah.
Things like that. And you think about it, yeah, these guys have to talk about controlling reality. They have to make decisions emotionally because not delaying a decision when you're lighting a company is a decision, right? And you'll have consequences of that. It's uncanny their intuition on picking the right thing to do and immediately abandoning the bad things, like Howard Hughes. You know the history of it, probably Elon Musk to some degree,
Yeah.
and
It,
they have incredible minds as far as kind of shifting reality, controlling reality.
it's known
Um,
as fluid intelligence as well too. Like you can do an IQ test and that's something, but if it's fluid intelligence, thinking on your feet is and that's what CEOs do. They're
right,
constantly thinking, I could do this or this. Which one should I do?
and you get
Right?
the intuitive flashes. They are deaf. Their
Yeah.
higher selves are their
Yeah.
intuition is super on, and they just know that this is the shit and making them instantly. And
That's a
so
great point.
that talent that and I think we all have it. We're all just got to
Well,
open up that channel to our higher
Yeah.
self.
exactly. Bingo. That's amazing. Let's get back to the slides and see. There's probably a few more that we want to have a look at because
Yeah.
we haven't got to the gases yet. So we're looking at the 212. You can keep going, Brendan. Let's just see what's past all this stuff. So they're talking here. Okay, so here's some of the different circuits, right? Your guys were asking about Class A and Class B, and so Class A, peak grid voltage drive equal to or less than the grid bias. So that means the tube stays on all the time and never shuts off, and that's the definition of Class A. When you go to Class B, the grid bias practically at cutoff and grid swinging voltage higher than the bias. So basically it's shutting the tube off, right? Is it shutting it off? Like, is it shutting it off on one side? What's going on the other side, you guys? Because it does swing from zero back into the higher voltages and stuff, right? Oh, okay, we'll move on then.
Would that be a push-pull circuit, Ed?
No.
Okay.
You can see that, like, for example, the Class B is used for radio frequency oscillator or power amplifier, but if you run a power amplifier in Class B, now you don't have high fidelity, essentially.
Are they turning it off and on? Is that the basic
Yeah.
idea?
Yeah.
They're flip, so the current completely shuts off or turns on depending what they do with the grid. So is that Class B, the on off? So
Yeah.
we're in our switching mode, abrupt switching
Right.
mode.
Yeah,
Yeah.
exactly. Yeah.
Oh, okay. Where A, you're always on, so it's gradual. Everything amplifies. So that kind of makes sense. You're
Yeah.
trying to work it like a switch.
And then it says the power required of the modulator for complete modulation of a Class C amplifier is half the direct power input to the plates of the Class C amplifier. So it's just different ways of operating things, essentially, right? Let's carry on, Brandon. Let's see what else we got. Yeah, so there's your Class C, right? Grid bias below cutoff, essentially. So it would be pulsing, just pulsing, which is good for free energy, right? That's exactly kind of what you want, but not good for sound, for fidelity and whatnot. So this shows that tubes can be used in multiple different ways. And I know, Alan, are you aware of the inverted triode, where you actually run the plate and the cathode differently? You invert them. Have you guys ever seen that?
Well, I know that what's his name has a patent, but
What's his
about
name?
about a
Steve
grid
something.
being used. I'll think of his name. Go ahead.
Yeah, and I'm trying to remember the guy's name too. But there are operations where they've inverted things. Because I actually looked at inverting a 6AS7G. That was the good one. And the tube curves are quite linear. So this one here, what tube was this one again?
Okay. Well, I was thinking of David Burning.
Oh, that's it. Yeah.
One of his patents is a grid.
Yep.
I can't think of the word, but it's a unique circuit.
I think it's the inverted triode that I'm just
Yeah,
talking
yeah.
about. Yeah.
Right.
It is
Gotta be
Burning,
that.
and there's a few other guys that do it, but he's definitely the one that has made it popular. And he said he patented it too, eh? The circuit.
Yeah.
Yeah.
That's one patent, and the other patent he has is the output transformerless.
Okay.
Zotl, ZOTL.
Is that one a push pull or is it a single ended?
No, well, he did make actually a single ended version, I think, with an 811 tube.
Okay.
And everybody loves it who has one. Well, they'll never let it go. So maybe we should put out a new version of that.
Yeah.
That would be great because everybody wants one.
Yeah.
But his commercially available ones are and were available as push-pull.
Yeah.
And now he's working with this linear tube audio, LTA,
Okay.
they're reproducing his designs.
Oh, okay.
But they're different.
Yeah.
But they're still output transformers with the same modulated power factor, high frequency.
Yeah.
So you don't have hysteresis.
Yeah, and see, with push-pull, the power supply is much, much easier to design. But the problem with push-pull is it cancels out all of the even order harmonics and only leaves the odd order harmonics, which tend to sound very lean and harsh. And musicians have known this all along. So Chip talks about the mega, what is it called? The mega, there's a guitar amplifier that.
Oh, the Mason Boogie amplifier, the
Yeah.
Ampeg. Yeah,
Yeah,
well, Marshall, all of them had big
yeah,
tube amps, but
exactly.
Carlos Santana's had a little Mason Boogie amp. The damn thing was that big. He put a mic in front of it, but made his guitars, his Stratocaster sound like a violin, right? It would
Yeah,
just harmonics pouring off of it.
yeah, exactly. Because and that's so one of the things when they talk about OTL amplifiers, I've actually got the book, Alan. I'm gonna, oh, I may not have it here, but I've got the book, and it says natural musical harmonics. That is, I can't remember the guy now. You'll know. He built all the OTL1 and OTL4 and
Oh yeah. I mean the other manufacturer of
yeah,
OTLs.
yeah, he did them really early.
Oh, you mean the first one, huh?
They're
Yeah. What's his name?
They're push pull though.
Mhm.
There never was a single ended one.
No.
I like I said, I designed one, and I've got some designs of a few of them, but it's all from the Russians. Like it's all totally from the Russians, right? Yeah, yeah.
Yeah, I'm gonna look it up while you guys go ahead.
Okay.
Didn't
Yeah.
Bruce De Palma have a output transformerless design? Do you know Bruce De Palma, the guy that came up with the N machine?
Really, an audio
No,
amplifier?
I didn't know
Yeah,
that.
yeah,
he
designed he designed some pretty fancy audio. I came across the schematics in my archives a while back, and I was like, "Holy
Wow.
smokes!" Because I was looking for the some of those, Faraday disc end machine type stuff, and his stuff came up, and then I found some schematics for one of his amplifiers.
Oh,
And I'm
cool.
pretty sure it didn't have an output transformer, so we should have a
I'm gonna
look
look
at
that up. Okay, Futterman.
Yes, exactly. I've got the book from him. And in there, it's called Natural Musical Harmonics, I think is in the title or something of that book. And it's highly, highly, highly recommended to read that. That was one of the first, I think I read it in 1985 when I was learning about how to design amplifiers. And because the output transformer, again, is, if it's not designed correctly, you're not going to have great sound. It's just how it comes. And the really good ones are really expensive.
Yes.
Well, they use a lot of tubes in parallel to lower the impedance. Yeah.
Yeah. Where my design, I only used a single tube, and I got 18 watts out of it, which is more than enough single-ended power to do, power up anything.
With just two?
One.
Okay.
Single-ended.
So again, how did you do that again?
I'll share I think I've got it in my phone because I'm not at my house anymore, right?
Okay.
I think I've got it in my phone, but I'll share the circuit with you guys and show you what I did.
All right. Really interesting.
There's a lot of cool stuff that I did. I included a crossover because I run everything, tube stuff I run from 80 hertz and up, and 80 hertz and down, it's always solid state, right? So I built a 80 hertz and up crossover into it as well, right? So there's a bunch of stuff, but it does use an interstage transformer though.
Oh, that's good.
Yeah, a really, really good one with like 4-core pure silver on both sides, nano amorphous material. Just saying this too, for people to understand, the very best cores in the world come from Hitachi. And that's the ones that my guy uses. Do not use the Chinese ones. They're not as consistent, and they're not up they're just not as good, essentially. And then he uses all the best silver too, silver on both sides, 4 core, 4 C cores in one design, right? Yeah,
Mm-hmm.
the best of he builds the best of the best, and he's
So,
in Malaysia.
so question for the whole group: what do we know about the Bedini amplifier? I mean, he built it 40 years ago, and I guess the company is still up and running. It
No.
was an audio amplifier, and obviously he was interested in Z field.
Yeah.
Did you say
And
Bedini?
so-
Did you say Bedini? Bedini.
Yeah, John Bedini.
Yeah, yeah.
Yeah, I mean, Bedini will. We need to do a bunch of shows on him for sure, right? So,
Oh, yeah.
yeah,
And this would
let's.
be a tie-in with his amplifier concepts, and
He
see
made
if
his
he's
own.
dragging Z field out of with his damn tubes. Yeah.
No, he made his own. He made his own transistors. He baked them in the oven.
Oh wow!
Yeah,
Oh, that's interesting.
yeah, yeah.
Interesting.
And he had his amplifier on the market for a while. You can look it up.
He
Bedini
did.
amp.
Yeah, there it is. And it's somebody else is taking it over. I don't know if it is original design or not. That's why I was asking.
Right.
Mm.
Q series 10 preamp. Let's see more, Brandon. Let's
Yeah.
or maybe click on the amp one. The big, maybe the big one.
That
No,
big
down
one there?
below. Yeah.
That one
Oh,
there?
yeah.
There.
The
Let's see what it
100.
says on the front there.
Yeah.
Okay.
The cube. Okay.
Q series.
So it almost looks like Carver, where he's
Look, yeah.
actually Class A
Well,
for
that's the same logo.
Class
you
A feed forward design, so forward feedback, hey?
So where's the tubes?
Doesn't look like there are any.
Yeah, I think
No,
it's
no.
for solid state. Yeah.
Bedini
What
didn't
the
do
hell?
tubes. He was all solid state.
Yeah.
I misunderstood then, because I listened to Tom Bearden talking about Bedini's amplifiers. I understood Bedini's object was to drag Z field, 0 point field, with all the goddamn potpourri of harmonics that come with it once you tap the field,
Mm.
to use
Yeah,
as an
let's.
audio
Oh,
amplifier, and
Brandon, could
he's
you go
very
back
rich.
so I can look at that?
Look at,
Oh,
look at the
the
specification.
the circuit itself, the picture. Yeah.
Mhm.
Doesn't
See,
look like much to me, actually. I wouldn't want to listen to it, to be honest with you.
Where's the goddamn power transistors?
Yeah.
Mm.
Yeah.
I didn't really look at John's audio side. Like
Those look like IGBTs, insulated gate bipolar, I think, right?
Yeah.
It's push pull, I can tell right away.
Yeah, quasi.
It's semi, and there's no much of a power supply, so this thing probably sounds like crap. But sorry, guys, but
I like to find out what his original concept was and
yeah.
why he
Well,
built it.
why don't we
Yeah.
dig into that next time? And when we do Bedini, because I'd love to have Carmen in on one of the Bedini ones, because I think she's had quite a bit of contact, and her father did too, big time, if I remember correctly. Yeah.
Mm.
Let's go back to our original presentation here. And what are we looking at here? So this is the 212, and you can see how the lines are, they're good, but they're not quite as good as the 845. They're not quite as straight, and the spacing is not bad. It's the one good part about this tube, though, is as you go up into the plate or the grid voltage, more towards 0, it's quite linear.
It
It's
goes
still,
to hell on the positive side. Geez.
well, that's why you never operate a Class A in the positive side, right?
Yeah.
That's the whole point of a single-ended Class A. The best sound comes from a single-ended Class A. The next best sound comes from push-pull Class A. And then it just go, well, if you don't include the OTL amplifiers, because the OTLs are a whole different matter. They can be very transparent, even in push-pull, they can be very transparent.
And Eddie, these vacuum tubes that we're looking at, it relates to the Philadelphia experiment. Is that right?
Well, they used vacuum. Yeah, they didn't use this tube. We can look at that tube another time. It was a 6L6 for the most part that they use, which is is it a tetrode or a beam or a full pentode? I think there's different versions of the 6L6 too, if I remember correctly.
Oh yeah, you're right. Yeah, that's right. Beam tube. Yeah.
Yeah. So they're not as linear. They're not nearly as linear. And that's an interesting point. You know, if we were to reproduce the Philadelphia experiment, which is something that we maybe should try, we might want to use triode tubes to see if the linearity of them is going to affect the experiment more. I would suspect it would. I don't know. What do you guys think about that, Paul? And Alan, look at he's thinking. He's got a thinking cap on.
Yeah. No, I mean, but Preston, early on anyway, as I said last time, he was insistent on push-pull because you needed that back and forth action to stimulate the ether.
Okay.
Exactly, like a pump wave. Exactly.
Yeah. I could see it. Yeah, I think it'd be worth, it's not about audio quality at this point. It's about how do we get the best signals out of the mind and project them into the field, right?
Yeah.
But then I said, then later on, years later, probably, I brought the issue up again, and he said, "Oh yeah, well, single-ended is okay if you do it right."
Well, there you go.
But there's other ways of doing it too. Like I said, the distributed line amplifier is something else that he liked because of that. Because he had 5 tubes in that distributed line.
Transmission line sort of setup.
Yeah.
Yeah, gotcha.
It's like you'd have to look up the term to get more specific officially.
Transmission line acoustics. It's built into the definitive acoustics.
This is a distributed line, which I think was used to get better signal to noise ratio at original purpose.
Right.
But Preston used it for his mind amplifier type of research.
Yeah.
So I guess the key question is, what are you trying to drive? It's one, have all this tube technology to amplify and create a lot of power, trying to drive something. I think the critical question is what we're trying to drive, quote, the ether or ZPE or whatever.
Well, a speaker, right? A speaker actually is the same thing as magnetohydrodynamics, because it's actually, and as a matter of fact, there's a type of speaker called an electrostatic speaker, which are the very best of the best. And they operate exactly the same way as our aura, as we do, essentially.
Mm-hmm.
Right?
So we're trying to drive, let's say, a layer of heavy particles on the speaker. Where's our transducer to really affect the vacuum?
Well, what I'm working on now is such a transducer.
And you said a clue when you were mentioning Hutchison using Van de Graaff generators and things like that in the environment. And we're making a lot of ions, and now we want to drive them. Okay, right. And that may be your connection to the ether itself, driving that itself. So you have a charged surface and vibrating that, a charged crystal vibrating that. So you have your technology to do the driving, which can be standard stuff. The transducer to influence the vacuum and do warping of space-time and things like that. I think you're gonna need some heavy particles in the system to be driven. So that's a clue.
So I've actually developed a direct drive setup to drive electrostatic speakers. And I know Dr. Roger West, who is from Sound Lab, and he builds the best electrostatic speakers in the world, period. When I talked to him about what I wanted to do using a single-ended Class A 845 and a special output transformer to take it from single-ended to push-pull operation, because when you operate a electrostatic speaker to make it have good resolution and low distortion, you have to operate in push-pull. all speakers need to be operated in push-pull. All speakers on the planet that are not push-pull speakers all have one flaw. The motor system pushes it out, and then a suspension system pulls it back in, or an air spring connected with the box. That is absolutely non-linear as hell. They sound like crap. I've designed using Dyne Audio, the best speakers in the world, and they do sound good, but when you listen to an electrostat or even a push-pull planar magnetic, like I have the Pink Floyd speakers, there's no, I mean, absolutely no comparison whatsoever. So the thing about it is the transducer. So Alan was about to talk about something about a transducer here.
Well, and right, a Corona Wind speaker or a plasma speaker.
Ooh,
Yeah.
yeah.
Okay.
So when you
Now,
say
I don't know if you
electrostatic speaker,
guys have ever heard of
Yes.
John Iverson.
Or Magnot. Magnot had the, you're talking about the.
No. Well, that's I'm talking about a full range version of that.
Yeah.
John
I've thought
Iverson.
about a million times about a full range version of that. So what have you?
Okay, well, the problem is the ozone, because it'll kill you.
Yeah, and it killed Nelson Pass.
Didn't he?
He got harmed by his version of it. Yeah, he had to be hospitalized at a show, I think.
Yeah,
He was demonstrating it at a hi-fi show, and they had to take him to the hospital.
Right.
yeah, that's why I tell them to hold your breath.
What was the other guy? He ran helium into it. So he used
Oh.
helium
Yes.
in the plasma.
Oh, that's another version. Yeah,
that's the best
that
version.
helium
probably
speaker,
wouldn't
right,
get-
Paul?
I actually have the manual for that speaker, Plasmatronics, I think.
Plasma, yeah, right.
That
Right.
one's very good.
That is,
Yeah.
Wouldn't get as much ozone out of that one.
if we could reproduce a full range
the-
version
yeah.
of the Plasmatronics, maybe with backup subwoofers, probably for really
Well,
low
the thing
frequency.
is, what we want to do is make one that produces negative ions, because
Oh,
then
yeah.
it's going to be healthy.
Make a
Well,
healthy
No.
we can still make
Wow.
ozone if you have enough ionization.
Bingo.
And what was that? What was that, Maury?
You still can make ozone if you have enough ionization going around.
Yeah, yes.
Just a lightning strike.
We want to. How do you make it all?
Ionization occurs by the waterfall, right? That's why it
Yes.
smells like fresh air.
How
A
do you
little
make
bit
it all
goes on you.
negative, though? Do you know
You're
how
not-
to make it all negative?
Well, once you're ionized,
Negotropic?
you're gonna have both, right? You're gonna have
Yes, you're going to have both,
positive
basically.
So, but when we're trying to, if the goal is to modulate the ether, right, the ZPE, get all that activity, then you're using your heavy particles, oscillating them on electrostatic speaker. I had this question: is there a charged surface that is indeed electrostatically charged? So now we're vibrating that.
Yeah.
That would then influence
The
ether.
diaphragm.
The
Yeah.
diaphragm
Right,
is
the diaphragm is charged itself.
with
Yes.
DC. Yes,
With DC.
and then the
Negative.
grids
DC,
are push pull.
Isn't it negative DC too to the diaphragm itself in an electrostat? You can operate in different ways, but that,
Right. Well, the
Yeah.
common way is it has the grids on either side of this very, very thin plastic sheet.
Yeah.
Is what it modulates the
Called the
sound.
stators. Those are the stators.
Yes.
Yeah.
Mm-hmm.
And are they charged? So we have plasma that's actually getting oscillated by the sound.
Basically, Moray, like in my design, normally they used transformers to take the voltage that comes out of the amplifier. Let's say it's 30 volts peak to peak. You need 6,000 volts peak to peak on a electrostat to make any kind of efficiency. So the transformer itself has to do the step up. Now that's kind of a non-linear way of doing it. So what I proposed was, let's take the high voltage swing that 845 has and use that high voltage swing and swing, about 1,000 or whatever. Now we've only got to go up 5 instead of from way down below. So now we can create a much better output transformer. But no one has ever built a single-ended to push-pull type amplifier setup. Because even Dr. Roger West, when I proposed it to him, he came back and he said, "That's an excellent idea. Let me know how it goes." And I've got contact with those guys because of these humanitarian projects. And yeah, so there's something to all of this. But going back to the plasma type speaker, and being able to create a full range one with negative ions. What is that thing in the desert that creates negative ions called, that was built in the 50s? I'm just trying to remember the name of it.
The Integratron, is that what you're thinking?
Exactly.
Yeah.
The Integratron is designed to exactly do that. Negative ions, that's where your good health comes back, and all the magic stuff happens essentially.
Or
So
you can
what you
take one of
said,
those ionic wind,
Yes.
ionic
Yeah.
air filters. If you modulate one of those with an audio signal,
Yeah.
yeah, yeah,
that's what you get.
Aren't there some
exactly.
speakers that actually put out vortex to simulate a subwoofer type of thing, or a woofer
Oh
with
yeah,
ions and moving the air that way, as opposed to an actual
there
vibrating
was a
surface?
company that they, I don't know if they still do it anymore.
Bones,
There's rotary.
uh,
Eastern Voltage.
and to
They
create
that's the name of the
low.
company. They created a subwoofer that worked on an arc inside a box.
Yeah,
And
That
then,
came from T. Townsend Brown, the acoustic fan. I think there's a lot of mystery about that. Nobody really knows what it was, but I think that's what it was he had developed a really high fidelity Corona wind kind of speaker like that.
so
well,
that's
he's
what we need to
now
do.
learning to vibrate the ions in the
Yeah,
environment.
right.
Hutchison makes ions by the Van graph in the environment, and then everything else. It could be that simple. You want to start influencing the ether, get some ionization going and vibrate the
Yeah.
ions in that plasma to really affect the environment.
And
And then
also
and
what
then
Hutchison is doing too is he's using bootstrapping, so that DC is at a very high potential. Then when he puts the AC on top of it, it's at a very high potential, and that's part of the magic, and that's how amplifiers work. Like that's the whole premise of
Who are you
amplifiers.
talking about there,
Um,
Roger?
John
West?
Hutchison.
I lost my train of thoughts.
John
Who was it you were just
Hutchison,
describing?
Putting the
John
AC on the
Hutchison.
DC.
Bootstrapping. That's
Yeah.
bootstrap. I learned that from the Russians. Like
No,
that's
who did you say somebody was doing that?
John
yeah,
Hutchison.
yeah, Hutchison. Yeah,
Hutchison. Okay,
yeah,
I
yeah.
didn't catch the name yet.
Yeah, so yeah, Hutchison is doing exactly that. He's creating this very high DC potential, and then he's oscillating it on
Modulating it.
top. So
Mhm.
now, if this is at 100,000 volts and you've got 2 volts up here, now you have a 200 or 102,000 volt swing, essentially, right? And that's where the resolution and some of the magic happens, essentially. Yeah,
Or just modulating, vibrating the ions in that environment, because you just made a glow plasma, you made an ionized environment, and now you're working it, right, with your driving signal. But
yeah,
what's important is you drove the ions in that environment, and that's where you're going to influence the ether.
yeah,
Mhm.
That's your key. So the rest of it is to get that signal up there, get the power up there. But where if you focus on, my goal is to drive the ions. Now you're on the Thierry Moray's principle. Then you're activating the ether, and now you're starting to activate into that energy and everything else. Not to mention influencing biology,
yeah.
Mhm.
because we respond to ion currents. So is the electromagnetic system different if it's driven by ions as opposed to just electron vibration? I pose that question in
Mm,
classical electrodynamics. No. In
yeah,
quantum electrodynamics, yes.
yeah,
Hugely less, because we have a different substrate particle that interacts with the vacuum differently
yeah.
between electrons and ions. And so the ion driving the ions is the key to activating the ether.
That's a great nugget, Moray. Yeah, amazing. Because you said that many times actually, because that is kind of the key. That would be the clutch that Ken Shoulders talks about, right? The
Well,
clutch.
in that case, they made something sophisticated. That's a large object compared to the elementary particle. They made something, and that something could involve a vortex ring of ion motion.
Yeah,
That
bingo.
made the EVO.
Yeah.
And then we listened to Bob Greenyer last night. The Russians are way beyond with more sophisticated modeling going on inside of that. And there's plenty of room to do model because we're well above the size of an elementary particle now when we're at the micron size.
Yeah. Yeah.
And so you have structure there. It could be as simple as the plasmoid, the vortex ring closing on itself. If there is ion motion in that ring, and it's not just the electron spiraling on, but the ions undergoing that spiral, I think that's where you have the excess energy being trapped in the EVO.
Yeah, and we also know from Ken Shoulders, I think it's 10 to the sixth ions that you need to create those charge clusters, and 10 to the negative, what,
Now,
11 or something?
that was basically
11.
a charge to mass ratio
Yeah,
measurement.
exactly.
And it really the coincidence of always being at the same as the electron or positron if you make a positive one. He said that's a key to the pair production. This is a fundamental thing that the vacuum is giving you that's more than just the individual particles that went in to comprise it. There's something else going on. Ken says it's like I built a macroscopic charge out of the fabric of space itself. He
I,
Right.
intuitively felt that's what
I,
that's what it was. It was way more sophisticated
I
than a simple vortex ring in
I
his
think
intuition.
the key to everything is changing the permittivity of space itself,
And
right?
that word is used for how the degree of polarization. So if the vacuum is naturally polarizable, right, it gives rise to
Mm.
pair production for starters,
Yeah,
right? Then it is polarizable, and that's most of the
Right.
ether theories are that way.
yeah.
It gives,
Right. It's
I
an
guess,
energy density gradient.
Yeah, gradient. Thank you. Bingo. It's
Mhm.
always a
Potentiate.
gradient. Yeah.
Yeah.
A potentum, Joe Firmage would say. A
Yeah.
potentum.
Yeah. That's awesome. Yeah. Wow.
Well,
Um,
Maury, you could take it one step further. And I tried several times last night to get Bob to go down this path. And we will have another meeting with him and we'll shepherd him a little bit more carefully. Once we get to this toroidal construct that he has demonstrated so well in 3 or 4 or 5 or 6 dimensions, if you go all the way to Pavel and take his work and integrate it with Bob Grenier, you're now looking at a micromolecule that does have classical spin and
and
inertia
counter spin and
and
counter spin.
inertia.
And
And
yeah.
now you can tune the space-time metric.
Mhm.
Now you can shape the curvature of space by mucking not only with potentially electron toroidal clusters of about 10 to the 11th, like Ed says,
Yeah.
but quark gluon plasma clusters. You go down one additional level, down to the subatomic level, and now you with sentient three-dimensional time you can control the quark spin on a macromolecule. I got this whole shit from Grok here in the last few weeks, which you guys
Oh my.
might want to see eventually. It's absolutely mind-numbing. It is so
well,
cool.
by the way, on three-dimensional time, you should dive into Dewey Larson, one of his books. He
I've
was
got to.
obviously
I know it is.
inspired in the 50s. I mean, he's coming up with this all on his own, to incredibly inspired. And I said, don't look yet because I wanted to hear your information independently. But now
Yes,
it's time
yes.
for you to look and see how well it aligns with everything you learned on this, because
Yeah.
Yeah.
your source of information was what channeled information for 3D time, right? It's such an alien concept for our existence, our physics. And all of a
I know
sudden,
it's
we have him coming up with it independently and building up a following around starting in the 50s. And all of a sudden, you're hearing something similar. And what I like to see is connecting the dots between the two models, between the
yes.
both of you independently coming up with that and now seeing what aligns in similarity and what doesn't. Get some intuitive
and
insight. What's going on?
and
Something's going on that keeps resurrecting this concept that's
Yeah.
beyond our perception. We
and
Well,
perceive linear.
and maybe try and relate it back to subquantum kinetics, because it's actually those etherons at 10 to the minus 65th, I think we said the other day, that are
yeah.
actually the start of this whole
which
chain
which
of
which would
events,
lead me to
right?
what's his model of space and time. So you have
Yeah.
postulates have to go into any theory you want to make, right? So if you want, we perceive the Newtonian world, so we naturally want to do it that way. That's how our imagination and our visualization works. And then Paul might do likewise. I don't know. Does Paul construct a lot of theories in physics, construct space and time? They have something more fundamental. If you want to construct it from the ether, fine. Or do you have activity, space time exists, Newtonian, and you have activity that exist in space time? You can make ether theories either way. You can keep your Newtonian physics, then the big advantage there is the derivatives are nice and simple. The disadvantage is it doesn't seem to explain everything. Certainly doesn't explain warp space, right? Or you can explain it if you make your theory appropriately, but put your postulates in it and explain it. I don't know what Paul does as far as what is his backdrop. Does he have, is space-time derived in his theory, or is space-time assumed like
Well,
Newton
you have
did,
you have to
and then
understand that.
the ether exists, giving us.
So in Paul's model of the Turing wave, you basically have the Turing wave oscillating between space-time, which is our reality, and time-space, which is the non-local. Now, I mean, other people might call that non-local side another dimension, but I do not like that term at all because it is not correct. We live in one dimension. We all live in this universe, and that is one dimension, essentially. There are different it's just the terminology that they use. It's just like black holes. That terminology is all wrong. It's a vortex singularity. There's a mother star at the center of our galaxy, and there are vortex singularities at the center of the sun, the planets, in probably including us, if you really think about it, right?
Well, we didn't quite hit the fundamental question, which Chip was probing with the 3D time. The fundamental question is, when you make a theory, you can like assume a backdrop, and then have your ether active in that same space-time backdrop and give
Well,
rise to all physical
the,
phenomena. That's one direction you can go. Another direction you can go is I'm making space-time from my ether in that model, and a number of physicists do that, proposing that space and time evolve from something more fundamental. So my question wasn't, well, what's reality? That's not my. That's I know the answer is I don't know, but the question is, somebody makes a theory, they all put in postulates, and they can take either direction on how they want to construct their theory. So that's strictly up
the,
to the
so
person. What are my postulates? So
so the,
that my go ahead.
so
You
the,
understand the essence of my question is,
yeah, but so
did
the
Paul
3D
assume
time, so the 3D time part of it comes in the time space side, where you have three dimensions of time and one essentially of space. And those three dimensions of time allow teleportation, time travel,
and Paul has
everything.
all this in his theory, has this counter, or that's another three dimensions, so to speak,
Yeah.
in this time space domain. This is part of Paul's theory.
That's, because I had contact with him a couple times. That's my understanding of how it all works. Yeah.
Well, then it's a far richer substrate than the Newtonium as far as what you want to assume. It's just an
It-
assumption
It
what you
is.
want to put in.
exactly. And
So
and
now
that
we're back to Chip, right?
so
We're
now
back to history dimensions of time.
well yeah.
Yeah.
But
But
one thing
I
though,
like,
sorry, Chip. One thing though is quarks are particles that are put in a particle accelerator and busted apart. They're actually not real things that we can engineer with. So you have to be careful about your terminology there. We are talking about spin and counterspin, like Pavel says, and the magic always happens at the center. So same thing with the compact fusion reactor. You've got one thing twisting this way, another thing twisting this way, and right at the focal point, you have this charge cluster occur. That's where all the magic happens, and that's where the 0 point
And
energy, right?
and standard electrodynamics as originally derived by Dirac, the electron positron state. The pair production, this is your two counter rotations, and some say spin is a hyperdimensional rotation. There's your fundamental activity. You always are having that pair business going on, always.
Yeah,
So
because
that gives us a fundamental assumption, at least, of what is the fabric, the ether.
so
Dipole. Yeah.
yeah, so essentially those etherons are basically coming from time space, the non-local, into our reality, creating that Turing wave, and then which is a dodecahedron standing wave pattern down in the subquantum at the very beginning of everything, which is like the main building block. And then after that, it just gets built up from that. But it's always the same, like you say, donut or torus shape, with it trying to twist onto itself as these structures. But again, there's rotation and counter rotation, because that's all of Pavel's theories essentially, right?
Mhm.
Yeah. One
Well,
thing
that's a common theme, and that's a good one to put in as a postulate. I got to have the pairs.
Yeah,
Yeah.
Regardless of how you want to model it from then on.
So the
Yeah.
pairs, you have to think about them as like I said, and the way that Paul describes it is they're called virtual pairs when they're in time space, and then when they come into our reality, now it's a particle, right? But when it goes back, and in Pavel's theory, his energy is like a sheet, and when you roll it up into this donut, now you have a particle. That's basically the gist of his theory, right?
Yeah, I'm going to probe a coincidence here. Paul postulates time space. Is everybody agree? You've been studying subquantum kinetics. That's a foundational point in Paul's theory. Does everybody agree with that? Because I wasn't aware of that. But I have not taken a deep dive into Paul's
So
work.
the best thing to do is read Secrets of Anti-Gravity Propulsion. I mean, Brandon is working on the subquantum kinetics part. If you really want to understand how all this works, especially the electronic side and anti-gravity and how it affects everything, that is absolutely the book to read. And I've got 80 pages of handwritten notes from Paul's work that were spread out all over the world. And now, nicely, Jeff has actually digitized them. I haven't gone through them yet to make sure everything's correct. And I think there's something we have to add on the end to finish it. Then we'll give you guys this stuff and you'll understand things a lot better, because my handwriting is horrible. It's hard to read.
It'd be great
Do
to
you
get
have
that in a single document.
Yeah, exactly. Yeah. And do you have those papers, Murray?
I don't think so.
The Violet's
I'll
papers.
send them. No,
I'm-
the
I'm-
papers that I wrote on Paul Violet, they were actually given to Elena Denon. She was the first person in the world to get them, then Dr. Sala, and then like NORAD and a whole bunch of other places they went.
Yes.
NASA.
So what I'm trying to drill in on is it's actually much simpler. Did Paul on his own come up with the time space domain?
No, as
And
far
then
as I
it's part
know,
of his.
not in he not in subquantum kinetics. He doesn't mention it. But that's just something added on that Ed is trying to develop with subquantum kinetics. He doesn't.
Okay.
Paul didn't go into time space unless he talked to someone else about it. He said there's no
Thank you.
time.
Maybe talk to Dewey
to.
Larson.
Right.
Well, that was my
I'm
thing.
trying to say who came up with what, because Paul felt that he developed a pretty good ether theory, trying to explain phenomena. And my question is, what idea came from whom? But so if Paul did not come up with the time space, I still have my questions about his postulates. But everybody's kind of agreeing. Okay, we have this other domain, time space, right? The trips at 3D time, right?
Yeah,
You're saying the same
non-local.
thing, right?
Non-local.
And
Yeah.
now, and then Dewey Larson or others. I don't think non-local existed when he was alive. That didn't get accepted to the 80s, right?
Yeah.
And so
I guess, sorry, Marie, I guess the answer to this is partly Paul and partly me, essentially,
right,
is
and
where
that's
this comes from.
fine.
Yeah.
Go for it. Whatever other
But I
ideas.
did have contact with him about it, and discussions and such, right?
Right.
And you have to understand too that Turing wave is oscillating between time space and space time, but there's an orthogonal flux also involved there, and that's where all of the energy from the ether actually comes from, right? It's always
Right. Because now you have the extra dimensionality for an orthogonal flux to even exist, right? That was, Wheeler took one step, just one step,
Yeah.
got one extra dimension by taking that step, and he says just derived it. He calls it the already unified field theory, and right away with just that one extra dimensionality in it for electromagnetism. Very much similar to Klein-Kaluza. They added one more dimension.
Yeah.
You have wide open phenomena that can occur. I think the
Um,
tough phenomena was non-local.
yeah.
Whenever
And
you do
and
non-local stuff, that's the part that blows people's
so
mind.
the other thing is that this information also comes from David Wilcock and Stevati Aerospace. And there's probably, there's even more, there's more
Oh,
to that.
I could say just any of the channeled work. People are receiving information,
Yeah.
and it does seem to be a common theme to the information they're receiving.
Yeah.
And
I, I've
minimally, there's high dimensional phenomena. And
I've meditated and seen the Turing wave many times. In fact, with Chip, we've had meditations where we've gone down to that level, jumped down to that level, but I saw it way before we started doing that. It was
yeah,
just
and the
intuitive. Yeah.
little bit you shared with Alan Turing, you're applying his idea, the Turing wave, because it can create structure. What Turing derived is basically working with some nonlinear equations and
Yeah.
trying to see how biology can so. And he said, "Wow, I'm observing self-organization arise just from some nonlinear equations and that." So in
Yeah.
a way, he foreshadowed Prigoghine's work, which
Yeah.
people had trouble saying, how does self-organization occur in a system? And so Turing in a somewhat primitive way, but because he did it in the 50s, right? He actually was the first to show how
Yeah.
self-organization arises straight out of the math on a
Yeah.
nonlinear system, right?
Um, so,
So now
And then,
applying that, you can apply that into any system, and most of
yeah,
this is nonlinear
yeah.
anyway. And so
So,
you
that's
can apply
information.
the
so,
ideas.
so,
So all your ideas are valid, and it's even valid to give them credit for calling it a Turing wave. But that wasn't Turing's original idea. Was much simpler than that. It was just a mathematical description of self-organization in differential equations.
so where also this information ties into is a classified teleportation document. We went through some of it. I don't know if you were with us that day, Moray, but we went through it and recorded it. It basically talks about how everything that is the magic part is in the subquantum level and it's in the non-local side, right? So that's where the magic happens. And what I've sort of intuitively thought is that you've got these etherons that are coming from time space to space time. These etherons are actually carrying that information back and forth, right? It coming from the non-local, it's bringing it into our reality, creating this Turing wave. The Turing wave creates itself and then it disappears again and it goes back into time space again. Then it oscillates again. Every time it oscillates, that's your blinking universe at I don't know, a terahertz frequency or even higher. Um,
Higher. Yeah.
yeah, but every single time it does that, it's like a camera taking pictures, and those pictures are Akashic records, essentially. There's only one truth, that's the Akashic, and those are being recorded, right, because of those blinks.
That's the
And
non-local aspect, right?
that's exactly right. So that
So I
paper,
like I like what Ed is saying in terms of a single dimension, where it's almost like a super force, like Nassim Haramein talks about. I mean, you got a super force. Well, you have a super dimension of sorts. I
but
don't
it's not,
necessarily,
but it's not just one dimension, Chip, because there's 3 dimensions of time and
of
one of
course,
space. So you actually
yeah,
have 4 on each side, right? Or 4, not maybe. See, the dimension thing is actually wrong too. I don't, the terminology just bothers me because we really
yeah.
only live in one dimension, this universe. So this is the thing. Every single Turing wave in this entire universe is pulsing at exactly the same rate. If
In
it
this
doesn't,
universe,
in this
not
universe, if it
not
doesn't
the next
pulse,
one. Yeah,
exactly, if it doesn't pulse at the same rate, now you're into a parallel universe,
yeah.
which is a different dimension. That's the only time you really truly have a different dimension in my terminology, at least, essentially.
Yeah. I don't think I'm willing to go quite so far as to mash together, conflates time and space time in a recursive reciprocity. I tend to see time is completely fundamental to space. Space is emergent from the three-dimensional time field, which is buried with consciousness at the subquantum level. And this is why this topic is apropos for this group, because the Turing wave also answers the question of wave-particle duality. Well, how the hell does that work with the slit
Yeah.
experiment?
Yeah.
Well, the Turing wave is particles in a wave. That answers a lot of things. And yes, it may be a caricature, it may be a goddamn cartoon, but it's a way for us to visualize
I've
and
been
help us get to the next dimension level ourselves. Or I think as fifth dimensional beings, we will much better understand this. And so we're kind of teasing ourselves as a carrot and a stick. We're moving ourselves along. But one thing I wanted to go back to real quick that I found really interesting that Bob Greenyer was talking about last night. I threw a spitball at Quark, or I threw a spitball at Grok and said, what if I could create EVOs out of quarks? Holy shit. You
But
realize now I can
could you
control
tell me?
spin and flavor and
Can you tell me what
everything.
your definition of a quark is? Because I still have a problem
It's a
with every time
particle.
you say that.
Yeah, no, of
Um,
course, a subatomic particle in this classical theory. I'm going to base it on that for now. It has no mass, so you has no inertia, and it's subject to the Heisenberg principles and all that kind of shit. But if you clump them and use Pavel's concepts of dimensionality in a toroid field, multiple toroids spin in all directions, and then you bring in Morey's concepts of creating an ionic wind within that clump. Now the thing has inertia, omega, and an angular velocity, which
yeah,
is time, and
yeah,
an angular momentum, which is what? Gravity.
yeah,
Now I can
yeah.
tune the goddamn space-time symmetric with my mind potentially, because
Using
time is sentient, and we also got told that by those guys. Time is sentient. I can shape and tune the space-time metric, the curvature of space-time, using time to control gravity in a closed loop where the grid reference is determined by gravity itself.
yeah, because time itself is we're in the heliosphere of our sun. That is actually what's dictating our
Well, it's
time.
unique. Yeah, it's unique. Yeah.
When we move out into a different scenario, time is completely different. And Elena talks about that, how time here is different from time necessarily in a different spot, essentially. It's because of that. If you want to go back to how propulsion works, we use a vacuum plasma bubble sheath to make this stuff work. Well, that sheath is that's exactly what our aura is, essentially, right?
It's an event horizon, I would offer, yeah. And so the point I wanted to just finish up with real quick, Bob mentioned last night he thought that it was possible to create these quark gluon plasmas with EVOs. Did you hear that, Moray? I almost fell out of my chair because I'm thinking I cannot make quark gluon plasma to make myself a 10 to the 11th ball of quarks that I can manipulate time and gravity with. That requires trillions of degrees. Nobody's going to do that. But last night I heard Bob Greenyer say, I can create quark gluon plasmas with EVOs. I'm going, holy shit. Now I can create a gun, if you will, a EVO gun cannon, like maybe Hutchinson does.
That's
Now I
exactly
can
what it is.
I can go to the next level down in the foundation of the universe, and I can do this I can create EVOs with quarks. Shit, I'm golden.
Yeah,
I can do all
but
kinds of
here's the
stuff.
thing: it's the etherons that are actually creating all of this,
I would agree. And
right?
again, that's your nomenclature point, and it's a very good point. But in terms of falsifiability, in thinking
See,
we're just spitballing here, right? This is a goddamn thought experiment. But in terms of falsifiability, we can now start to use some of our good instruments, telescopes and various other things, to look for temporal shearing, XYZ shearing
Yeah.
in the time field,
See,
and
part of the
through
problem,
gravity effects and everything else,
Bob,
to get to this point where I can say, yes, I have an active
Bob,
temporal anisotropic field out there that is responsible for emergent gravity.
Bob Greenyer does not understand etherons, though. That's part of the thing. He's
I'm
got
glad
stuff
you
to
told me
learn,
that, because
right?
I got a little stuck on that with him last night. I wasn't
Yeah.
quite sure how
He,
far I
he,
could go.
he doesn't like, I mean, the people that have studied Paul Laviolette are sitting in this group, like literally, right?
Yeah.
Most people who say they know about Paul's work don't really know how it all works. Even people that are in other groups that we're in, Paul has said to them, you do not understand how this works, essentially, right? So
Yeah.
that's the thing. We have to start with the Turing wave and these etherons and what they're up to, because there's another person in one of our groups who is getting his PhD as a chemist. And I talked to him, and maybe at some point he can jump in here with us once he gets his PhD done, but he'll probably have the first PhD that is sort of related to subquantum kinetics. And he basically said that the chemical bonds are these etherons, essentially. And so
Yeah.
the etherons are doing the work all the way up the fractal scale, if you want to call it that, essentially. So, and we've tried to get Bob Greenyer in this group too. We almost had him in with Carmen that one time. So, there's that instead too, right?
Yeah, I can
We'll
invite him
work
in
on
too.
it. Yeah, we'll work on him. I think, it was our 0 Point group last night that Murray and I were listening in on.
Yeah.
That's the first time he presented. It was a very rugged presentation, and we'll tune it up. But one thing I did want to mention, I think the chemistry has got to come after the physics. The biochemistry, you're absolutely right on. Everything is still founded on physics.
Oh,
We're
absolutely.
the idiots that better figure the shit out before everything else falls in line.
Magnetohydrodynamics, that is the key. Again, you use that in the Lorentz force to fly the hover car. That's one of the ways that, he talked about 4 different ways to do it. That's one of the ways that it's done, essentially.
Well, if I'm flying a starship at 6 million times the speed of light, my DNA better be plugged into that machine.
As a matter of fact, if you guys really want to learn about it right now, all we need to do is go on my channel and watch a 5-minute or however long it is on there that talks about magnetohydrodynamics. It talks about even the ether wind that lifters use. It talks about exactly how this is done. And this is all from the Russians. This is all from the Russian hovercar program. Stuff that I got from Carmen, actually. She was the first person to send it to me because she knows Alexander Frolov, who's in St. Petersburg, right? So, and this is exactly where it comes from. And there's a little thing on my channel about that. When I put it, excuse me, when I put it on there, it got over 1,000 hits in about 2 days, right? And tons and tons of comments about, it's so simple.
I would offer that we should be putting vodka in all our baby bottles. Get these kids spiked up in a hurry.
Well, it's better than the formula. We know that now.
Yes.
Vodka seems to work good for the Russians, right? I mean,
something's working.
Exactly. Yeah. So, no, but it's great discussions for sure. But I think at the end of the day, it is at the fundamental level, those etherons, which are, I've said to Chris Beskar, I think that an EVO, ball lightning, and an etheron are all one and the same. They're just fractals of each other. And he said, yeah. He said, I think that's a great idea, right? So that's and those etherons, the definition of an etheron right from Paul Laviolette, because that's where an etheron comes from, is it's actually a conscious entity. So it's like you had said before, Chip, it's the conscious agent that creates all this stuff. And again, if that little etheron is flowing from time, space, picking up the information, bringing it into our reality, and going and get some more. And that's what they're doing, right? And it takes about 100 billion etherons to create an electron, and it takes about the same amount of electrons to create a charge cluster. So now we have some, it's all the way up the scale again, the same sort of structure, right?
We just need to
Well,
figure out where.
the arithmetic's a little off because the etherons are down at what, 10 to the minus 65.
Yeah,
They're
but
small.
well, that was
You
for
only
example
multiply by, you'd say 100 billion, 100 billion.
about
What
100
numbers is that?
billion. That's what
100
we looked
billion. Well,
up
that,
with Paul.
yeah,
Yeah,
so 100 billion is only 10 to the 11th. And we're
Yeah.
down 10 to the minus 65. So we're down to 10 to the minus 54. So we're still below the Planck length, well
Yeah.
below it.
oh
So
yeah,
I'm just
that's
running the numbers. I'm just
Mhm.
yeah.
by the way, I kind of can see the problem where there's kind of disagreement. It's really over the vocabulary. What is being held in mind by a particular vocabulary, like the word quark. That came out of trying to explain stability of a nucleus. And the weird thing about the quarks is they can't leave. The nature of their attraction is they're always they're not allowed to leave, right?
Yeah.
So you all of a sudden have a bizarre particle that's unlike any of the other particles that were invented by
But,
physics,
but
and they're saying, see, you can't prove me wrong because we can never get
yeah,
one out. Ha ha
but
ha! I have
but the
my
thing
imaginary
is,
particle.
but here's the
Uh,
thing: if you're trying to create coherence, is what you're trying to do when you're tapping the ether. You can't do it with a particle that has been smashed apart. That smashed apart particle might have some properties to it, but it has nothing to do with creating coherence to the ball lightning level, or so because
so
ball lightning can be huge, right? And they can be
so
stable.
So notice what I'm doing is integrating all. Where's the common thing we keep agreeing on, the common concept, right? We know fractal stuff is going on, so we have as below so above. Okay, we have that mechanism.
Yeah.
We have the pairs going on. Always seems to be in pairs. So that one we're all agreeing on, and the other was, well, the nature of charge itself as a plus or minus may relate to some type of hyperspin. That idea has been kicked around a lot, both in standard physics as well as in the esoteric realm. So we kind of have
It's
this common notion.
the
We've
monopole
seen, yeah,
is where it
that,
comes from, right?
but when we start using vocabulary, oh, quark law and soup and everything else, well, whose quark theory are you talking about,
Well,
right? That's not,
but
they're not even supposed to
so
come out, etc. The
this is
other
a sub.
idea,
Sorry, Maury, this is a subquantum kinetics group,
right,
and that's what my focus is here. So that's
right.
why I'm very careful about black holes, quarks. When you guys start talking about that, it confuses things. So what you're describing is perfect, because we do need
Well,
to come
well,
to
they're
common
right.
terms, right?
Right. And now that's the point I'm getting to. We have Paul's theory, and I'm just trying to get to the postulates of what is in his work and what other people are thinking of in their work. But you can see there are common elements to all these ideas. Okay, we can start to lock in on those, and we have Paul's ether theory, right? And I'm not sure what belongs to Paul versus what belongs to everybody else, adding their ideas on top of that. That
Well,
seems to be
again, I'll refer back to Secrets of Anti-Gravity Propulsion. There is no better way to learn about what he's describing, because here's the thing. This is why I'm involved with Stevati Aerospace, is because they said when I first talked to them on Zoom calls that we know how we can make it fly, but we don't have a theory. And the very next day, I said, I'm going to post the theory, which I did post the theory on David Wilcock's forum. And that's my connection. And that's where everything started with Stevati Aerospace, essentially. Stevati even has a hard copy of my 80 pages of handwritten notes. They have New Aerospace Technologies, which is a book that Alexander Frolov wrote that I was asked to have a look at to see if it correlated with subquantum kinetics. His ether models, the Russians' ether models connected with subquantum kinetics. And I came back and said, yes, they do. There's no question about that, right?
By the way, guys, as you've been talking, I was just putting together a document whilst you've been talking on a question I asked the ChatGPT the yesterday. So it's I'll post it on research, see if I can. So I just came up. It's just
Yeah.
it
There's
asked
the
me where I got the
biochemistry.
idea. It asked me where I got the idea from. So I said we were talking about electrostatic phenomena that allows spiders to fly, and then I thought of capillary action in SQK, and then so photosynthesis. So it seems to think it's quite a good idea. Anyway, I'll put it on
Yes.
ResearchGate and see.
You know what? There's like I was saying, there's something on my channel. It's like 2 minutes or not even a minute long. Why don't we have a look at that? Because it actually shows a plant creating oxygen, which is not that's photosynthesis, is it not?
Yeah, from your channel, Eddie.
Yeah, it's a short.
In the future, scientific projects will take about 10 minutes to complete. if I'm thinking of you just ask ChatGPT or whatever. Anyway, it's just a joke. Don't worry about it. What do you want, Eddie?
Yeah, I see. Just ask the AI give me the theory of everything so we can be done with this.
Yeah. Well, you know what? We don't ask the normal AI that, but we did program into the UFO AI that Dr. Ryan Wood had, and recently I asked it a question of the Turing wave, and it came back with not a great answer. So Ryan said, "Well, it doesn't have enough information." So that's when we plugged in all of Paul's information. It already had my papers and whatnot. It's a short, Brandon. One of the shorts.
And that's exactly how you train these AIs.
Yeah, exactly. And Brandon has been training it the 5.2 version as well. We've done a lot, and we did a lot with the Heart's fifth chamber with that. But it's this one, the plant. So just click on that. Yeah, the plant. Yeah. You guys see the?
Yeah. Little geysers of oxygen. Yeah.
So what's really interesting about that is if you look closely, they're very well spaced. The spacing is perfect.
Yeah.
Oxygen. You're saying that's oxygen, right?
Yeah. So there you have it right there. You have a plant who's got an aura, just like we, that is vibrating, and there's a direct connection to the aura using magnetohydrodynamics, which is a direct energy conversion, which all of life uses. Planets, us, plants, everything uses this magnetohydrodynamics. In 1985, when I was taking engineering, I bought an engineering Bible that is like this thick. And I immediately opened it up to the page of magnetohydrodynamics and marked it. But I didn't really understand why I did that until about 5 years ago when I started doing all this kind of research and went, yeah, something happened back then to mark exactly the magnetohydrodynamic thing. Again, with the Lorentz force. Brandon, there's another one on there. We don't have to watch all of it, but let's show you where this one about how magnetohydrodynamics and the Lorentz force is used to fly things. And this is something that I said to Chris Beskar one day. I said, so we're going to use magnetohydrodynamics and the Lorentz force to fly the hover car. And he said, yes. And it is
On there, that one there.
No. Keep going.
So that MHD was showcased in the movie Hunt for Red October. You remember the caterpillar driving the submarine?
Yeah.
Very same concept.
And actually, well, I won't say too much about that, but I've seen that before in the military. It's Brandon, you were almost at it. I think you went too far. It's not that one. But there's another one that should be right beside it. So go the other way. Where is it? Yeah, that one. Yeah.
Electrohydrodynamics, EHD, is not the same as electrodynamics. The field of electrodynamics includes both EHD and MHD, so all forms of EHD propulsion and MHD propulsion are also electrodynamic propulsion, but not all forms of electrodynamic propulsion are necessarily EHD or MHD. Electrodynamic propulsion is a useful term to distinguish MHD in a conductive physical fluid from MHD-type propulsion in a non-physical medium, such as the quantum vacuum.
And we know the magnetic
move on to the next section
magnetic
of this
fields
video.
go through everything.
MHD propulsion fundamentals. To begin, let us remind ourselves of how wings work. If you research the subject, how wings work, on your own, you will eventually discover that there is no one single answer to explain how they work. However, you will find all explanations revolve around the concept of creating a pressure differential between the top and bottom of a wing, with the aim being to increase the relative pressure on the underside of said wing, leading to an effect called lift. To clarify, the exact mechanism of lift really depends on the specific circumstances, flight environment, wing design, etc. Different mechanisms must be at work in different situations, or even multiple mechanisms may be active at the same time, or for the same wing or airfoil at different times, lower or higher speeds, etc. Now that we are finished re-examining how wings work, it is time to consider the meaning of the term Lorentz force. What is the Lorentz force? The Lorentz force is the repulsive force between magnets, or more specifically, it is a force that arises when electric current is at a right angle to a magnetic field. This occurs even for permanent magnets such as ordinary fridge magnets. In this case, the currents involved are created by the magnets themselves, as opposed to being created separately, as we will discuss with regards to MHD propulsion. These currents are also generally quite weak. It is worth noting briefly that the repulsive force you feel when trying to push a pair of magnets together is in fact the Lorentz force. A fluid can be accelerated, decelerated, or its pressure increased or decreased via the Lorentz force. In order for the Lorentz force to act on a fluid, the fluid must either be conductive already or made conductive in the moment, such as by ionization or the addition of electrolytes. In the case of MHD propulsion, oppositely charged electrodes are used to create the needed electric current through the fluid. A magnetic field is then passed at a right angle to it, giving rise to the Lorentz force, accelerating or decelerating the fluid. If the fluid is already moving, a Lorentz force can be used to either accelerate the fluid further and thereby decrease its pressure, or to decelerate the fluid and so increase its pressure. If you are looking for an even more detailed description on the Lorentz force, you can easily find one on Wikipedia. We will put a link to said description in the description section of this video below. We will also leave a link to a comic book style explanation of how MHD propulsion works by Jean-Pierre Petit. Despite the comic book style, the explanations given are very accurate and thorough. Okay, so far we have covered this: what MHD propulsion is, how it works, and covered some of the fundamentals of MHD propulsion. Now let's move on to the next part of this video: how MHD propulsion functions in an atmosphere. Now remember, electric and magnetic fields can only act on a conductive medium. Therefore, to operate in an atmosphere, an MHD-propelled vehicle must first ionize the air. This can be done in one of several ways. but one of the most efficient methods is known as high-frequency pulse discharge, or HF pulse discharge for short. This is where an alternating current at radio to microwave frequency or higher produces electromagnetic radiation in fields that ionizes air or other gases very efficiently. The ionized air then forms a conductive sheath just off of the surface, which absorbs all or most of the emitted radiation. Once the air is ionized, it can be moved via electromagnetic forces such as the Lorentz force or via an ion wind effect. This is where EHD propulsion, ion wind propulsion, and MHD propulsion can sometimes be confused with each other because in some vehicle designs, both forms of propulsion can be implemented on the same vehicle to maximize efficiency. Also, different versions or iterations of a vehicle might use only ion wind propulsion, only MHD propulsion, or both. The airflow created by MHD acceleration or ion wind is directed over an airfoil creating lift. This can be airfoils in the form of more or less conventional wings. Alternatively, a saucer-shaped Coanda effect airfoil provides greater lift than a conventional wing and is well suited to MHD or EHD that creates a wind without the need to move the entire vehicle nor even the airfoil. Think of the saucer airfoil as a wing wrapped around the vehicle. MHD propulsion can also come in the form of a MHD plasma jet engine with a very high power density. That is, a small device will produce very high thrust. This is in sharp contrast to ion wind thrusters, which have a very low power density and therefore typically very low thrust. MHD propulsion in space. The simplest and easiest form of MHD space propulsion are MHD jet engines, or rather MHD rocket engines. These can utilize the Lorentz force to directly accelerate a cold plasma. Alternatively, radio frequency discharge or microwaves can be used to superheat a gas into a hot plasma state, which is then kept off the walls via magnetic fields, which involves Lorentz forces. The hot plasma is then allowed to escape as with a conventional chemical rocket engine. There are advantages and disadvantages to both. Both can have a high thrust and a high efficiency. Though using a hot plasma will generally give a higher thrust but lower efficiency unless the plasma is extremely hot, as in fusion temperatures. In the not-so-distant future, we will utilize MHD space propulsion that pushes off of the quantum vacuum directly.
Bingo.
To avoid confusion with strictly atmospheric or water-based MHD, we sometimes call this electrodynamic propulsion. Empty space is not actually empty. It is filled with extremely short-lived particles, usually called virtual particles. However, the term virtual particles is a misnomer and historical misnaming, as these particles are not fundamentally different than ordinary particles. The only difference between the so-called virtual particles and ordinary particles is lifetime. Though virtual particles are exceedingly short-lived, most things happen over very long periods of time in comparison, so the activity of the virtual particles cancels out and can be safely ignored. However, for electromagnetic fields or radiation with a very high energy, very high frequency, or both high energy and high frequency, these virtual particles cannot be ignored. Therefore, ultra-short and intense electromagnetic pulses can interact with these abundant and ubiquitous particles, particularly the short-lived electrons and anti-electrons, also known as positrons, a kind of antimatter. These ultra-short and intense electromagnetic pulses can then be used to create Lorentz forces on the electron-positron plasma, creating thrust.
Yeah, so it's a really good kind of description of the different terminology and how it works. But you notice how there's that donut. There was always that torus donut above the craft, essentially, right? So it all goes back to that donut or the torus shape, right?
Yeah.
which starts with the letherons, and then it just moves up the whole
Yeah, the
scale.
Lorentz force comes out orthogonally. Yeah.
Yeah, and so the Lorentz force and magnetohydrodynamics are used for not only flight, but for us, life, everything. The planets, the stars, the mother star, everything operates on this principle essentially, right? So that's kind of why I put it up there. And that's from a great channel too, Astronaut, I think it's called. And there are stuff in my playlist, because that's just a little clip from a really long
Yeah.
one, essentially, right? So yeah, cool.
There's one little
Mm.
thing I might correct in the airfoil discussion. It's not a reactive force, it's a pressure differential.
Exactly. Yeah, exactly. Yeah, yeah. That is exactly correct, Chip, for sure. Yeah. We know that's the Wright brothers, basically, right? Yeah.
So
Very
the
cool.
important thing is to tie it to what's the nature of inertia, because you want to be able to do hairpin turns without being slammed against the wall. So that means you now really warp space time,
Well,
right?
actually,
Which involves
so
the virtual particles,
yeah, so what
etc.
happens is it's actually called a vacuum plasma bubble sheath.
It's the
And
bubble. Yeah.
everything within that bubble, there you don't get slammed against the wall. You don't feel anything, as a matter of fact. And Elena has described that as well too. When
Wow.
they accelerate past light speed and into whatever kind of speeds that they go, it's not like being in an elevator where you can feel it fall or whatever, right? It's you're anything within that bubble is sort of protected. So what is that
Right.
bubble?
So there you go. That's the missing part when you talk about magnetohydrodynamics, because there's nothing there in the classical EM theory that deals with plasmas that warp space-time and control inertia. That's where it ties to the zero-point energy ideas and all of that. So
Mhm.
there's a new concept that has to come into the theory to give you all of this. And one of the things from yesterday, what Bob mentioned that I resonated with. He says, and Ken Shoulder said the same thing, that inside of the plasma or the EVO, we completely are in a different space time.
Oh,
We're
absolutely. Yeah.
completely, which is, and so now notice the distinction between all those ideas being in the versus, oh, here's my standard electromagnetism, which is founded in our current space time, right?
Mhm.
There's nothing that changes that. You have to have an extra concept come into the theory
Mhm.
to
That's
warp
that's
space
like
time.
Cal Richardson's little vehicle, right? You've heard about Maury. We've talked about it in Salt Lake several times. That was a macro EVO bubble. Like Ed said, it was almost ball lightning that he was sitting in, and he flew it to the moon supposedly with his consciousness and everything else.
Yeah,
So that is time dilation. It's a local variation. You have that much gravity that you're playing with, either electrodynamically or magnetodynamically. You will create time dilation on a local scale. That
absolutely.
temporal sharing allows you to exist in a different dimension. You're not
Yeah,
going to get turned to mashed potatoes when you make a right angle turn.
yeah, exactly. And that's basically how they work. And that vacuum plasma bubble sheath term came from my stuff from Stavati Aerospace.
Yeah,
Like that was
yeah,
4.5 years ago when we were talking about this stuff, right? Yeah.
yeah. Chris Vescar's contribution to the science, I think, is understanding how to
Mind
structure
blowing.
this and
Yeah.
keep it stable. This
Yeah.
vacuum
Well,
bubble.
it's the coherent. It's back to the creating
Yeah,
that coherence. So that's where like when you talk about a quark being a particle that is smashed apart, it only lives for a short, tiny. It's not. You can't create coherence. You can't create ball lightning. You can't create charge clusters from that. But the spinning part of the quarks theory is correct. So
yeah,
it's like Murray says, it's about terminology. And
yeah.
same thing with black holes. I am adamant that they not call them black holes. We are all in one dimension here, but there are different densities. That's the difference, right? Yeah.
So different frequencies, maybe a potpourri of frequencies. each with their own informational
Well,
density.
exactly. So Elena's definition of density, density is actually the frequency of your DNA, how,
Mhm.
how it vibrates. So if you're at a 6 density, and let's say you're a 3rd density here, and you're at a 6 density, let's say in a different environment or lifetime or whatever, that's just the difference in your frequency. And you have to understand that there are 13 densities in this reality, this dimension that we live in
This
right now.
dimension. Yeah.
This dimension that we live in right now, there's 13. And the 13th density is source itself. So let's talk about the Anunnaki, where the Anunnaki came from, for example. They came through the portal at Arcturus. They teleported or interdimensionally traveled from one universe to the other. Now, in their universe, source is at 16. So whatever structure they have is going to have a structure of 15, because in our universe, source is at 13, and that dodecahedron, which has 12 sides, which is the Turing wave, is 12, right? So in the 16th density Anunnaki world, you have the geometry of 15, and that Turing wave is at a different frequency, essentially, right? Now, if you can match the frequency of the Anunnaki world, now you've teleported there. This is how teleportation works, right? So it's always about understanding the difference between the densities and the dimensions and all of that stuff. And there's no better person to listen to than Elena Denon about that. As a matter of fact, she's and even probably Dan Winter talks about stuff like that as well. I'm not sure if he talks about the density strip or not, but
Well, yeah, I think he broke out a little bit from what Elena originally published, where there were 13 dimensions with
yeah,
gradational densities within each one of those. That's the way she originally described it. She got herself in a lot of hot water. And I
yep,
think Dan Winter tried to ferret that out, but that's vocabulary again
yeah,
at this point.
exactly, yeah,
Yeah,
exactly.
I would view a dimension as just not only the frequency of the being that's participating, their DNA frequency, but there's also time flow, chronoflux is
Well,
very different in each dimension.
because the
Yeah,
Turing wave is all pulsing, every single Turing wave
exactly
in
right.
our entire universe is pulsing together, right? That's the key to it all, right? And as soon as you
Yeah,
start altering that, now you can time travel, you can teleport, you can do all kinds of magical things, right? Yeah.
yeah. And so I wanted to ask a little bit more. You had mentioned the Akashic record a
Hmm.
little before this, and Moray and I both are trying to proceed at some way to couple this fractalization from 10 to the minus 65th all the way up to subatomic quarks or whatever. There's a huge gap there. But, you know, I think at a perceptual level, if we view this local versus non-local and this
Hmm.
whole fractalization as a natural progression, then maybe we can view this as a single dimension at terahertz frequencies. And it would make sense where the beings themselves are biologically stable and comfortable with stratified frequency layers,
Hmm.
which also correspond to rates of time passage.
Exactly. Yeah.
And so that's where consciousness and time get conflated. And so that's why in my description of of dimensions, omega, the angular velocity is variable for each one of those dimensions. The rate of time passage is different for a ninth dimensional being as opposed to third dimensional being.
Yeah.
And they have a whole range within their dimension, a whole range of frequencies that they can exist at as well.
Well,
And
definitely in the higher ones. Yeah, for sure.
yeah, and
Yeah.
even these simple caricatures that explain the universe that they can give to us prior to disclosure, they always give us stuff that we have to interpret, break down, and make sense of, because they never can tell us anything directly. Thank you to the Prime Directive.
Yeah,
Like
we
we
have to
could
do it
trash
ourselves.
that.
Yeah.
We could trash the Prime Directive any day, as far as I'm concerned. You know, and so they give us these little hints, and by what Elena does so well is she describes these little things, and then we have to kind of read between the lines without going too far out of the guardrails to understand this whole big picture. And this is what's good about groups like this. We
Oh,
come in here and we
exactly.
spitball this shit around it, and we come out with some kind of sense of reality.
Yeah, exactly. Yeah, that's it. And
Now,
what are we doing?
we've
It's
gone.
our consciousness, right? All
Yeah.
connected.
So
Yeah.
we've gone over 3 hours. So actually, I have to
Yeah,
bow out
yeah,
now.
I'd say so too. Yeah, it's about
It
time to go.
was
But
very imaginative.
again, amazing.
What I noticed that is we say a word, and everybody has their meaning that they and all their ideas that they were attached to that word, and those ideas can be very different. So it's very
Yeah,
very interesting. So how the different points of view, or I look at it as a piece of an Escher staircase. You're locally, it seems to all make sense, but as soon as I try to match it up with someone else's, the whole globally thing doesn't make sense. And really, it's what is the concept being mapped to the vocabulary? It's for when you're really imaginative like us, different concepts definitely come to mind on the same word. And
yeah,
so it's easy to talk past each other. So
yeah,
I have to go, but
yeah.
the imagination is all there. So I really get a kick out of this group.
Yeah, we always
Uh,
have fun, that's for sure. And the things that come up and is amazing. Yeah, and it's because we're connecting our consciousnesses together,
yeah.
essentially, in and all the great stuff comes out of it. So yeah. So I think you better stop the recording, Brendan, before we
Okay. Well, thank you, everyone. I
yeah,
hope you have a wonderful rest of the day.
thank you.
I'll turn the recording off.